Greetings and warm welcome to the lecture on third lecture on numbers. I guess all of you guys are doing good. I'm glad that we're joining back for the third lecture. I'm glad that I'm here with you today. So let's understand what we did in the first two lectures on numbers. This is a third lecture on numbers. So here we go. So I guess all is well. So let's continue our learning on numbers. So here today we'll try and cover. Today let's try and already we covered this in the previous classes. Already in the previous class we looked at the classification. We did look at divisibility and its application. This is what we did in the first lecture. Previous lecture was more emphasized on LCM, HCF and its application, right? And the LCM models, there were 3 models on LCM and there were 2 models on HCF. We did spend sufficient time on that, and then we looked at a couple of minor factors like highest power of a number in n factorial, right, and things like that. So here now today we'll majorly focus upon factors and its application, and also we'll try and focus upon the remainders. These are the 2 important topics that we try and do today. But before we do that, we'll also take a look at how to find the units digit of a particular number, using the cyclicity as a concept, right? These are the things that we are discussing today, maybe about 3 major things. The cyclicity, that is to find the unit digit of a number, and then we talk about the factors and some of its application. Then we look at some of the remainders and its theorems. Let's try and cover this maybe in about 2 hours time. Right, here we go. So okay, let's get started. Guys. If you have any of your doubts, you can post it on the Telegram group. So I will try and address some of them as I while I'm taking this particular lecture. Some of you might get some doubt, so you can always post it on the group. So I'll try and address it either during the lecture or could be after the lecture. It'll get addressed. That's one. Second, I guess all of you have taken the UOM 7. Some of you would have written the UOM 7, which was in the new pattern. If not, try and take the UOM 8, which is in the new pattern of CAT. That is a 2-hour pattern of CAT, 40 minutes per section. Right, here we go. Let's get started. So what do you mean by cyclicity of units digit? So let's try and understand this. For example, if I have a number 2, I have a number 2 raised to power 1. Let me write it like this. I'll raised to power 1. So I may have raised to power 2, raised to power 3, raised to power 4, raised to power 5, and so on. If you look at the unit digit, just focus on the unit digit of these numbers. 2 raised to power 1, unit digit is 2. 2 raised to power 2, let me fill this here. 2 raised to power 1, the unit digit is 2. 2 raised to power 2, the unit digit is 4. 2 raised to power 3, which is 8, the unit digit 2 raised to power 4. Write the unit digit, don't write 16, write only the unit digit portion of it. That becomes 6. 2 raised to power 5, now that's nothing but 32, write only the unit digit, which becomes 2. If you're aware, write it raised to power 6 as well, raised to power 7, raised to power 8, raised to power 9. Let's quickly write them, because for 2 most of us would be pretty comfortable writing those numbers. So if you see this, okay, 2 raised to power 6, 64, therefore it's 4. 2 raised to power 7, which is 2 raised to power 7, which is 128, therefore it is 8. 2 raised to power 8, 256, therefore 6. 2 raised to power 9, 512, therefore it is 2. See, point here is, okay, just like the calendar has a cyclicity of 7, that is Sunday to Saturday, Sunday, Monday, Tuesday up to Saturday, again back to Sunday. Very similar to this. Here also you find a cyclicity here. Here also you find a cycle. Now cycle of 4. Now that is 2, 4, 8, 6. Another 2, 4, 8, 6. Here I'm talking about 2, 4, 8, 6. Then I'm talking about 2, 4, 8, 6. It continues. Hey, what do you mean? What do you mean it continues? For what I meant here is 2 raised to power 1. The unit digit of 2 raised to power 1 is also equal to unit digit of 2 raised to power 4, which is also equal to unit digit of 2 raised to power 9. You just have to understand this concept once. Then you can solve any problem built on this. To find the unit digit of an exponential number would become pretty simpler. Right now, so what do you mean? What I meant here is this. The unit digit of 2 power 1, I'm asking you to refer to this. 2 power 1 is same as the unit digit of 2 power 5, which is same as unit digit of 2 power 9. This is what I meant by the cyclicity. Cyclicity is nothing but, what is the cycle? Cycle is 4. If cycle is 4 means what? Look at the common difference. Common difference is 4, friends. Common difference is 4. Similarly, you can write another one. Similarly, we can continue, extend this study. So what do you mean? Unit digit of 2 power 1 is same as 2 power 5, which is same as 2 power 9, which would be same as 2 power 13. Why? Because the common difference has to be maintained as 4. Okay, similarly, you can roll it now dot dot dot. It's an infinite series. It goes on. Unit digit of 2 power 2 would be same as unit digit of 2 power 6, which would be same as unit digit of 2 power 10, which would be same as unit digit of 2 power 14. Yeah, what is this? Again, the same common difference for maintain the common difference for the unit digits will match. Here I could see, I could show it here 2 power 2. What is unit digit of 2 power 2? 4. Yeah, what is unit digit of 2 power 6? 2 power 6, which is nothing but 4. Likewise. So likewise, you find that it's a cycle. Now I understand. Abruptly, if I ask a number, hey, what is the unit digit of 2 raised to power 37? What is the unit digit of 2 raised to power 37? What do you do? Power cycle. Therefore, you go by the power cycle. What is the power cycle for 2? Power cycle for 2, 4. Therefore, divide this by 4 and check where the cycle is standing, where the cycle is standing. In the sense, what cycles of 4? Remove all cycles of 4. Check where the where the pointer is pointing to now. All right. So therefore, you say that okay, 37 divided by 4. You take 37, you divide this by 4, 4 9 times 36, remainder is 1. Therefore, you say that man, 2 raised to power 37 is nothing but unit digit of 2 raised to power 1. It comes under the family of 2 raised to power 1. Alright, it's same as this. So you don't have to by heart what is 2 raised to power 1. That comes pretty naturally to you. What is 2 raised to power 1? 2. Therefore, you say that 2 raised to power 37 is also nothing but 2. Why did I divide by 4? Understand this once. Why did I divide this by 4? Because the cycle for 2 is 4. Just like a calendar. Say, all right, now today we are on Tuesday. All right, now assume that today we are on Tuesday. All right, we are on Tuesday. If I say that, hey, what would be, all right, what would be 10th day from today? What would be 10th day from today? Simple. I will remove a cycle of 7 because calendar has a cycle of 7. I will do 10 divided by 7. I will get 3 as the remainder. 3 third day from today. It is as good as third day from today. Today we are on Tuesday. Assume today we are on Tuesday, Wednesday, Thursday, Friday. Therefore, you would say that, hey, 10th day from today is nothing but Friday, because 10th day is as good as the third day. So what did I do here? Cyclicity. I'll let cyclicity because I knew the calendar cyclicity. Therefore, I divided by 7. I divided this by 7. Right now, similarly for months also we can do. What would be 25th month from today? Simple. Cyclicity for calendar, cyclicity for months is 12. 25 divided by 12. The remainder becomes 1. It's as good as the next month from today, which is nothing but October. 25 months from today is going to be October. Right, things like that. All right, now things like that. So that's what all right I mean by the cyclicity. Oh, you understood the cyclicity like this. It's there for every digit. Therefore, what do you understand? Cyclicity for 2 is 4. All right, cyclicity for 2 is nothing but 4. All right, let's understand the cyclicity for 3 now. What would be cyclicity for 3? All right, let's understand them. Let's package them. Cyclicity for 3. After that, I'll go to 7. There is a reason. Cyclicity for 8. Then I will discuss. All right, now so this is one cluster. I'll come to this why I'm making the clusters like this. Then let me tell you the cyclicity for 4 and 9. That's another cluster. Then I will do the cyclicity for 5, 6. All right, let me put in the order. So, yeah, let it be. All right, now let me do the cyclicity for 5, 6, 1, and 0. Cyclicity for 5, 6, 1, and 0. Or let me write it as 6, 5, 1, and 0. Let me put it like this. Let me put it like this. Now these are the other digits. Okay, let me explain what it means. So what I meant here is, hey, all these digits have the cycles of 4. The first cluster, they have the cycles of 4. They have the cycles of 4. Think about it. Let's write for 3. 3 power 1 is 3. 3 power 2, the unit digit is 9. 3 power 3, unit digit is 7 because 3 power 3 is 27. 3 power 4, the unit digit 81. I'll let therefore 1. The next again, I'll let now 3 power 5, it becomes 243, which is 3 again. Likewise, I'll let now likewise you can continue this particular study. 3 power 6, 7, 29. Therefore, it is 9. You can continue this study. Technically, what I meant, look, the cycle is 4. Cycle is 4. Just like the way we understand for 2, it is same for 3. It's also same for 7, friends. All right, now 7 power 1, which is 7. All right, 7 power 1, which is 7, then 9, all right, then 343, all right, then it is going to be 1 here, then again it is going to be 7 here, and so on. 8 also same. I'm writing it quickly for you. 8, all right, there is a 4, there is 2, and there is 6, and then again all right, it becomes 8, and so on. Therefore, you understand that, okay, the cycle, which means you'll have 4 distinct digits for 8. However, for 9, take a look at 9 here. All right, take a look at 4 here. Let's take a look at 4. 4 unit digit, 4 power 1, 4. 4 square, 16, therefore it is 6. A 4 cube, 64, therefore back to 4 again. Right, then you say 4 power 4. All right, 4 power 4, 256, therefore 6 again. So therefore, what you are trying to say, man, the cycle size has reduced to 2. Cycle size has reduced to 2. Cycle size has reduced to 2. Every odd power of 4 ends in 4. Every even power of 4 ends in 6. Simple. Odd, even, the powers are odd or even. If it is an odd power, the unit digit is 4. If it is the even power, the unit digit is 6. Likewise for 9 here. Take a look at 9. So 9 power 1, all it becomes 9. 9 power, 9 power 1 is 9, 9 power 2, 81. Hey, what is 9 cube? 729. Therefore, back to 9 again. So it becomes 9191. Therefore, the cyclicity got reduced to 2. Now think about 6. Now think about 6. Cycle get reduced to 1 now. Cycle get reduced to 1. 6 power 1, that is 6. 6 square, 36. 6 cube, 216. The cyclicity is 1, right? Cycle is 1. Similarly for 5. 5 power 1, 5 square, 25. 5 cube, 125, and so on. Therefore, the cycle is 1. 1, all right, now it is 1. So 0, the cycle unit digit. If the unit digit is 0, cycle is 0. So what is you are trying to say? Cycle is 1. All right, therefore the cycle is 1. Therefore, we are trying to say that the cycle is going to be 1. Fair enough. All right, now that's a study there. All right, now that's a study I wanted you to understand. All right, that is the study I wanted you to understand here. Right, that's a study I wanted you to understand. Let's understand. Therefore, what you are trying to say, there are 4 digits which have a cycle of 4. There are 2 digits which have a cycle of 2. There are 4 more digits which have a cycle of 1. There are 10 digits, right? Now this is the breakup. This is the breakup of the cyclicity of 10 digits. All right, that's a breakup. Now what is that you need to remember? What is the executive summary? All right, the summary that you should remember, because you definitely find applications built on this. Quite a few applications built on this. I will not get into all possible application here, right? But then I will show you some applications. Maybe I will show the tip of the iceberg. I will show some applications, but wonderful and beautifully created applications are built especially on the cyclicity of 1. Remember, especially on cyclicity of 1. These 4 numbers are more important than the other numbers, 6510, because critical applications are built on these particular digits which are ending in 6510, numbers ending with the digit 6510. Fair enough. Let's take a look at this first. Let's understand this. All right, now what is the summary you should remember technically? Number 1, all right, the summary you should remember is that cycles which have the cyclicity of 4, the digits which have a cyclicity of 4, you should remember. Digits which have a cyclicity of 2, you should remember. Digits which have a cyclicity of 1, that you should remember. That's 1. But if you make a study, all right, now what is the LCM? See, the digits have a cyclicity of 1 or cyclicity of 2 or cyclicity of 4 or cyclicity of 4, right? Digit cyclicity of 2 is pretty simple, guys. 4 and 9 are pretty easy to remember. All right, it's no challenge. 4 and 9 are very easy to remember. In fact, they are perfect squares, right? They are perfect squares. 4 and 9 are perfect squares. Therefore, it's not very challenging to remember. All right, therefore 4 and 9 are easy to remember as well. These 2 numbers I'm talking about. Well, it's not very challenging because 4 and 9 are perfect squares, single digit perfect squares. Of course, 1 is also, but 1 is an exception. There is no brainer. Unit digit of 1 always remains 1 no matter what is its power. Right, yeah, good. So let's that's 1. So if I take the LCM of this 1, 2 and 4, if I take the LCM of this 1, 2 and 4, the LCM of these numbers become 4, right? So LCM of 4. Therefore, let's remember the summary at 4. At the 4th power, what happens? 4th power of a number raised to power 4. Number is nothing but the unit digit raised to power 4. What happens there? Let's try and understand 2 things. If n is even, what happens? If n is even, then what? If n is odd, then what? I'm talking about the unit digit. What I'm talking here, I'm talking about the unit digit of the 4th power of a number. All right, unit digit of the 4th power of a number. I'm talking about the unit digit of 4th power of a number when the number is even. Remember, it is always 6. It's always 6, except when the unit digit is 0. This is an exception. Exception is 0. N should not end in 0. The unit digit need not be 0. Otherwise, it's 6. Take a look at this. I'll mark this. Reality now 2. Look at this 2. 2 is an even digit. 4th power is 6. So 8 is an even digit. The 4th power is 6. 4 is an even digit. The 4th power is 6. 6 is an even digit. This is 6. Now another even digit, the number ending in 0 also becomes even, but then that's an exception. All right, that's an exception. Okay, take a look at the second pattern, friends. Take a look at the second pattern, odd. All right, unit digit of 4th power of an odd number. 4th power of an odd number is 1. 4th power of an odd number is 1. Take a look, 3. All right, I'm talking about this. I'm going in green. All right, now 3 unit, the 4th power is 1. 7, the 4th power of the 7 is 1. All right, 4th power of 9 is 1. 4th power of 5, so 4th power of 1 is 1. 4th power of 1 is 1, exception being only 5. Well, there are one exception to the rule. So now for the even, number ending in 0 is an exception. For odd, number ending in 5 is an exception. Now I want you to remember this particular summary. What is that? The digits which have the cyclicity of 4, the digits which have a cyclicity of 2, the digits having a cyclicity of 1. Point number 1. Second one, what happens at their 4th power? What happens at their 4th power? If I remember this, more or less we are game. All right. So let's look at the applications now. Quickly, let us look at a couple of applications before we move on. Right, let's move on. Before we move on, let's understand the application. Now take a look at this. I explained already. Find the unit digit of this. Let's take the unit digit of this entire number. Let's take one piece at a time. Hey, what is the unit digit of this? 4 raised to power 195. Simple. 4 raised to odd power. I said that it ends in 4. because 4 has only two cyclicity. Switch, alternate. 4 raised to odd power is 4. 4 raised to even power is 6. Simple. All right. 4. Hey, what is the unit digit of 5 power 20? It's always 5 because unit is 5 raised to power. Anything is 5. Okay. What about 6? 6 raised to any power is 6. 19 factorial is a power. It's a huge number. No doubt. No doubt. It's a huge number. But the point is the unit digit is going to be 6 for that. Unit digit is nothing but 6. Hey, what about 9 raised to power even number? 9 raised to power even number is 1 because we said 9 raised to power odd number. See, cyclicity. Hey, what is the cyclicity for 4? 2. What is the cyclicity for 9? 2. What is the cyclicity for 5? 1. What is the cyclicity for 6? 1. If I know the cyclicity with greater ease, I can write these numbers. Pretty simple example to start with. Hey, what is the sign between them? Plus. Maintain the sign. You got the unit digit. Therefore, add up these particular unit digit, which becomes 16. But I want the unit digit of this. I don't want all of this. Sure, you might have said the number is 16 here, but what is answer? Answer is nothing but 6. All right, your answer is going to be 6 here because I'm interested in the unit digit. Great. All right, now let's take a look at the next example. Let's take a look at the next example. Find the unit digit of 7 raised to power 23. Now let me break this into pieces. First, let's take the first piece here. Let's take this first piece. 7 raised to power 23 raised to power 723. Fantastic, beautiful question. So what does not matter? 7 and 2 does not matter. Why? Unit digit is always a function of unit digit. Or a tens digit cannot contribute to unit digit. Hey, but can unit digit contribute to tens digit? Yes. Unit digit can contribute to tens digit, no doubt. Unit digit can contribute back to tens digit, but not the other way around. All right, why? In the form of a carry. All right, there would be some carry there. Whenever you take the unit digit and you multiply it several times or add it, whenever you do, we know that all right, there could be a carry. The carry all right now might help to all right, might contribute to the tens digit and hundred digit, but tens digit cannot all right now backward is not possible. Tens digit contributing the unit digits, that's not possible, right? Yeah, therefore 7 and 2 does not matter. Therefore this question for me is as good as 3 raised to power 723. Fantastic. Now what I need to understand, hey, I look at this 3, I will say that what is the cycle for 3? Cycle for 3 is 4. Cyclicity for 3 is 4. That you should recall. All right, that you should recall from the chart. Cyclicity for 3 is 4, which means what? Remove the cycles of 4 because it is 723. I am not interested. All right, now so what is that? Remove cycles of 4. Remove cycles of 4. Let's see what is the tick, which means what you are trying to do. 723 divided by 4. This is what you are doing. What you are interested in after finishing n number of cycles. Where does this point to? It points to 3. Nothing but the remainder. What is the remainder? 3. Therefore, you say that man, 7 raised to power 3 raised to power 723 is nothing but unit digit of the 3 raised to power 723 is as good as saying 3 raised to power 3. Yeah, what is the unit digit of 3 raised to power 3? 7. Therefore, you say that okay, this is recorded as 7. Beautiful. This is recorded at 7. Now do the similar thing on the other side, friends. Do the similar thing on the other side. All right, let's do this first. Let's do this first. This is simple, right? 729 raised to power 529. Very simple. This is going to be 9. Why? Because what matters here? Only 9 matters. All right, 9 raised to odd power 9. 9 raised to even power 1. All right, 9 raised to even power 1. Right? That's what you do. Look at the next piece here. All right, look at the middle piece. Beautiful piece. This is beautiful piece. Right now, so look up, look there. All right, now let's say that all right, now this is done. Now what you have 4 raised to power what? The 4 raised to power even power is what you have. Right now you have 4 raised to power even power. Now look at this very carefully and meticulously here. Right now you have 4 raised to power even power. Right, 4 raised to power even power. The unit digit is nothing but 6. 4 raised to power even power, the unit digit is nothing but 6. If it is an into, do into. If it is a plus, do plus. If there is an into, do into. If there is a plus, simply do plus without panicking. All right, therefore you will say that this is 42. Unit digit is 2. Unit digit is 2 and 9. So it becomes unit digit of this becomes 1 because it's 11, but unit digit is 1. Therefore the unit digit of the given sum becomes 1. All right, unit digit of given sum becomes 1 here. Right, okay, take a look at this particular question. I want you to take a special attention, not on the top. This is repetitive, that's redundant. All right, top is redundant. Take a look at this question. I want you to take a look at this particular question especially. All right, this particular question, I'll give a minute, quickly walk through this problem. A minute, walk through this problem, then we'll go to the next concept. Quick, take a minute, walk through this problem, friends, everybody. Done, fairly done, good. All right, so what you would have done here, 8 does not matter. Let's do it together. 8 does not matter. What matters is 7. 7 has a cyclicity of what? Okay, let me 7 raised to power 87. So what is the 7 cyclicity? Cyclicity for 7 is 4. You should understand the cyclicity as 4. All right, therefore 84 is gone. It is equivalent of finding 7 raised to power 3. All right, therefore the unit digit is nothing but 3. Therefore from here you write it as 3. Cyclicity for 7 you should recall. Remove the cycles of 4. Remove those cycles of 4 there. All right, remove those cycles. Then you understand that the remainder is 3, which means the pointer is now pointing to 7 raised to power 3. Therefore the unit digit is 3. All right, fantastic. Let's take a look at the next one. 82 does not matter. What matters is 3. Therefore it is equivalent of 3 power 3 because the cycle for 3 is 4 again. Therefore 3 power 3. All right, which is nothing. All right, which is nothing but 7. Great. All right, that's what you have. Let's find the cyclicity for this. Let's find the cyclicity for this. If it is a multiple of 4, you should be taking it as a 2 power 4. Now listen to this very carefully. Listen to this very carefully. Hey, what is the unit digit of 2 raised to power 8? If I ask this, what is the unit digit of 2 raised to power 8? You understand that cyclicity for 2 is 4. You will divide this by 4 and the remainder is 0. 8 when divided by 4, the remainder is 0. What do you mean by remainder is 0? Cycle has completed. What do you mean by cycle completed? What is the cyclicity for 2, friends? You have 2 power 1, you have 2 power 2, you have 2 power 3, and you have 2 power 4. Then what? Then you will have 2 power 5, 2 power 6, 2 power 7, 2 power 8. Hey, there is something called as 2 power 0. It is not there. There is nothing called as 2 power 0. Cycle starts from 2 power 1, 2 power 2, etc. And now now you divide 8 by 4, the remainder is 0. Then what I should take it as? Remember, if the remainder is 0, implies that the cycle is complete. Cycle is complete means equivalent of 2 power 4. That's very important. Therefore, the unit digit becomes 6. If the number is divisible by 4, in K, when the number gets divisible by the cyclicity of that number, remainder becomes 0. If the remainder is 0, don't try to find out 2 raised to power 0. 2 raised to power 0 is not the answer. Answer is the final. What is the cyclicity for 2? It is 4. Therefore, you have to find that value. This is the catch. You need to be a little careful while dealing with this. Because that's what precisely happens. 32 divided by 4, complete. Division complete. Now don't write 2 raised to power 0 because the remainder is 0. No, what you will take it as? You take it as unit digit of 2 raised to power 4. Alright, what is unit digit of 2 raised to power 4? It becomes 6. Alright, therefore that's the required result. The unit digit is nothing but 7. Alright, 3 into 7, 21 plus 6. The unit digit is nothing but 7. Great. Alright, so you might have understood this very clearly now. By now you might have understood. Let's go to the next study. Right now it's a good warm up. We did. It's a good warm up. We did. Unit digit is pretty simple. Alright, unit digit is pretty simple, of course, but you will find the different levels of applications built on that, especially whose unit digit is 1. Alright, now you know that 6510, they have the cyclicity of 1. They have the cyclicity of 1. Be a little mindful that, alright, now a lot of good questions can be created on the numbers with a cyclicity of 1. We'll take it in the advanced lectures. Alright, now when I do the advanced lectures, we'll take this. For now, I gave the input on the unit digit, the cyclicity, concept of cyclicity. Great. Let's go to the factors study. Let's go to the factors study. Factor study. 3 things we'll try and learn. Of course, there are many more things already in the factors study, many more things. It's not that, but these are the 3 primary things. What is that? We'll find a lot of applications built on the number of factors of the number, because you use this in algebra as well, in the integral solutions, in various other places. Therefore, I say that, okay, the first 2 are important. Number of factors of a number is important. Expressing the given number as a product of 2 factors is important. Why? Because it finds its application even in algebra. Finding the number of integral solution, x square minus y square is equal to 220. Already find number of ways in which you can write already a number of integral solutions, or positive integral solutions, or non-negative integral solutions the equation has. Now it comes back to the factors study. When you get x square minus y square is equal to 220, it's an application of factors. Alright, therefore, although there are many things in factors, what is important to us, is most important to us, which has a versatile, already it has a diverse applications, is the number of factors of the number, expressing the given number as a product of 2 factors. Let's understand this. Hey, where do you come across the factors study first? Finding the number of factors of 2-digit numbers or a single-digit number, class 5. Alright, your association at finding the number of factors starts in class 5. Right? But yes, of course, when you become about 10-year-old, or 10 or 11-year-old, that is when your teachers will introduce how to find the factors of 24, right? Listing down the factors of 48, listing down the factors of 72 or 96, whatever be the number, whatever be that particular number. You in fact learn how to find the factors of every, say, 2-digit number when you are about 11-year-old. When you are about 11-year-old, that's where it starts. Fine, let's understand. From there, you go on to learn further and further and further. Factors come every single year. After that, every single year there will be a small thing. They get added to the factors till you reach your 10th standard. Right? It keeps added. Now let's understand what are the things, therefore, from CAT perspective or a management entrance exam perspective that you should know. Let's understand. Okay, let us list some of the factors before you understand. Let's list the factors. Firstly, let us write the factors of 18, friends. Let us list down the factors of 8, factors of 12, factors of 18, factors of 18. Let's write down the factors of, factors of 16, factors of 16. Then let's write down the factors of 36, factors of 36. Let's write factors of 25. Let's write factors of 49. Let's write some of these factors. Factors means the number which divide the given number. What is the first one? 12. So what are the factors of 12? 1 is a factor, 2 is a factor, 3 is a factor, which means 1 divides 12, 2 divides 12, 3 divides 12, 4 divides 12, 6 divides 12, and 12 divides 12. Right now, these are the factors of 12. Similarly, write for 18. I gave pretty simple numbers. Already it doesn't take much time to write. Let's write down these numbers. Hey, what are the factors of 18? 1 divides, 2 divides, 3 divides, 4 does not divide, 5 does not divide, 6 divides, right? And then 9 divides, and then 18 divides. Then 18 divides. Right now, these are the factors of 18. Hey, what about 16? Factors of 16. 1 divides 16. 1 is always a factor of any number, right? As we know, 1 is always a factor and the number itself is a factor, which means 1 and 16 are there for sure. And what are the numbers in between them, right? 1, 2, 4, 8, and 16. And 16. Factors of 36. 1, 2, 3, 4, 6. Then you write it as 9, 12, and 36. And 36. Right? Yeah. Let's take a look at 25. 1, 5, 25. What about 49? Look, there is something that I want you to observe. All right, now, so idea is, all right, why did I write these many exhaustive numbers? Are we going to count like this? No, we are going to understand the concept from here. Number one. All right, number one. So if the number is not a perfect square, take a look at this. If the number is not a perfect square, in this case 12, 12 is not a perfect square. It will have even number of factors. I'll come to the reasons why quickly. It would have even number of factors. Now look at the number of factors of this 6. You have 6 factors. All right, now there are 6 factors for 12. How many factors for 18? Because 18 is not a perfect square. If the number is not a perfect square, it has even number of factors. I'm not saying that it would be 6. No, I'm not saying that. It would have even number of factors. It can be 2, 4, 6, 8, 10, whatever. The number of factors, the count is going to be even. It will never be odd. However, if the number is a perfect square, 16 is a perfect square. Now count, it would have odd number of factors. Look at the number of factors here, 5. All right, now look at 36. All right, count the number of factors there, 9. All right, it has 9. 36 has 9 factors. Look at 25, it has 3 factors. Look at 49, it has 3 factors. Why? The reason being, these are all perfect squares. The perfect squares have even number of factors. Hey, you understand this in this class 7 or whatever, class 7, class 8, you understand this concept of what I'm saying. Even, all right, now, or if the number is not a perfect square, it has odd number of factors. It has even number of factors. If the number is a perfect square, given 16, 36, 25, 49, if the number is a perfect square, it has odd number of factors. Second thing, all right, now, and inside that, now look at this. Hey, look, write this 16 here. Hey, what is this 16? 4 square, which means it's a square of a composite number. 4 is a composite number. Hey, what is 36? It's a square of a composite number again. 6 is a composite number. Hey, what is 25? It's a square of a prime number. All right, 5 prime number. 25 is a square of a prime number. Right? 5 is a prime number. Hey, what about 49? 49 is also a square of a prime number. That's also a square of a prime number. Therefore, if it is a square of a prime number, it would have exactly 3 factors. If it is the square of a prime number, it would have exactly 3 factors. Remember, perfect squares have odd number of factors. Odd number of factors means what? It can have 3 factors, 9 factors, 5 factors, any odd number. But if it is the square of a prime number, it would have exactly 3 factors, which means if the number can be written as square of a prime number, if it can be written as a square of prime number, remember, it would have exactly 3 factors. But if the given number is a perfect square, if the given number is x square, the number is a perfect square, then it has odd number of factors. Odd factors. What about otherwise? If it is not a perfect square, it has even number of factors. That's something that you got to remember. Point number 1. All right, that's point number one. Now listen, all right, now another way of dealing with this. Another way. Point number two. This is another second point. This is 1 point. All this put together is 1 point. Which numbers have odd number of factors? Which numbers have even number of factors? Or which numbers have exactly 3 factors? Knowing that is point number one. All right, point number two. Those factors are equally distributed across the square root of the number. Now look at root 2. Look at root 12. Approximate. Let's approximate it. Root 12 is nothing but 3 point something. So it lies between 3 and 4. All right, it lies between 3 and 4. Simply take it as 3.5. There is no hard and fast rule while I'm taking it as 3.5. Lies between 3 and 4 right now. So it's here. Lies between 3 and 4 is here. Well, this would be the number. The number lying between 3 and 4 will be here. Something like 3.x. That what is that? Square root of 12. Square root of 12 lies between this. If it's a number line, the square root of 12 lies here. So what I mean to say? I mean to say that, hey, number of factors before the square root of 12 will be always equal to number of factors after the square root of 12. Number of factors will match on either side. The number of factors are going to match. Look at 18. Look at 18. Hey, what is 18? 18 is 4 point something. 4 point something, which means on the number line it will be somewhere here. 4.x. 4.x. What is that? This is square root of 18. Well, that's square root of 18. That is 4 point something. Okay, 4 point something. Therefore, again, the number of factors before the root of the number is same as the number of factors after the root of the number. After the root of the number. Take a look at 16 now. Take a look at 16 now. Okay, what is the square root of 16? This number itself. This is root 16. But number of factors before will be same as number of factors after. Number of factors before the root will be same as number of factors after. Of course, this time the 4 also qualifies because that itself that also is a natural number. Therefore, that also qualifies. Similarly, for 36, you can observe the fact pattern. So this is nothing but the root 36. This is root 36. Number of factors before 4, number of factors after, that's also 4. That has to always match. That has to always match. Point number 2. Just remember these 2 points out there. These 2 points out there. What? One, we talked about what kind of numbers have odd number of factors, what kind of numbers have even number of factors. Point number 1. Second point that we discussed is the factors are equally distributed across the square root of the number. Factors are distributed equally across the square root of the number. Okay, point number 2. Another one. Okay, let's answer this before I proceed. Let's answer this before I proceed. Answer this. I'll give a minute, friends. I'll give a minute. Go through this. Answer all 3 questions. Just 2-digit numbers. High school question. Put 3-digit number. It becomes adult question. Nice number. First, let's do 2-digit number. Yeah, well, you might have solved it by now. Let's take a look. Find the number of 2-digit numbers that have odd number of factors and those have even number of factors. Firstly, how many 2-digit numbers are there? So number of 2-digit numbers, smallest is 10, the largest is 99. Largest is 99. Therefore, how many numbers are there? 90 numbers, not 89. Don't take the difference. Difference is 89. I asked you to count. Difference plus 1 is the count, right? Therefore, there are 90 numbers. I'm asking today, man, out of these 90 numbers, how many have odd number of factors and how many have even number of factors? Odd is very simple. The number has to be perfect square. Number has to be a perfect square. Means what? 10 comes here, 11 comes here, 12 comes here, 13 comes here, 14 comes here, 15 comes here. Yes, 16 comes here. Why? It's a perfect square. Perfect squares have odd number of factors. What is the square? 4 square comes here, 5 square comes here because it's a perfect, already it's a 2-digit number. 6 square comes here, 7 square comes here, 8 square comes here, 9 square comes here because all these are the 2-digit numbers, right? Therefore 36, 49, these are the numbers I'm trying to say, right? These are the numbers that we are talking about, 64 and 81. All right, these are the numbers which are odd, which have odd number of factors. The perfect squares have odd number of factors. Therefore, how many? You are saying that 6. Six of them have odd number of factors. Therefore, what remaining of them? If six have odd number of factors, remaining out of 90 would have even number of factors. 90 minus 6. All right. Therefore, the remaining 84 have even number of factors. Simple. All right. That's how you look at it. Now look at the third question, which is a subset of the first question. As we discussed, the third question is the subset of the first question. Find the number of two-digit numbers which have exactly three factors. This time, author is talking about which have exactly three factors. Which will have exactly three factors? The square of a prime number. Here it is. Square of a prime number. What is that? 5 square. Well, what is that? 5 square. Square of a prime number. 7 square. Square of a prime number. Therefore, what? Only two numbers. Well, therefore, the answer is 2. Answer is 6 here. Answer is 84 here. And the answer is 2 here. Pretty simple ones. All right. Now you want to do an application question on this. Nice application question. Make it a 3-digit number. All right. You can change the 2-digit number to a 3-digit number. It becomes a nice application question for management entrance exam. Just change the 2-digit to 3-digit. But the concept I already told you. Pretty simple. Perfect squares. All right. Perfect. All right. Now you look for the number of perfect squares. You will get the answer for the first one. Second one, when you look for the perfect square, should I know the numbers like 16, 25? No, you should just know that 4 square is a 2-digit number, 5 square is a 2-digit number, so on. Let's do only the first one, friends. Let's do only the first one. Change this 2-digit number to 3-digit number. Let's just do the first one. Find the number of 3-digit numbers which have odd number of factors. So what is the range here? Therefore, 100 onwards up to 999. Up to 999. Between this, which means how many numbers technically? Technically 900 numbers. Out of these 900 numbers, how many have odd number of factors? That's a question. How many have odd number of factors? All right, odd number of factors. So what is that? The number should be perfect square. This itself, the first number, 100 itself. Therefore, what? 10 square. Then 11 square. Till where, friends? Till 31 square. Because I told you in one of the classes, one of the lectures before, 32 square is the smallest smallest 4-digit number, which is a perfect square. 1024. Therefore, 31 square, which is 960, 100. Therefore, all at 10 square, 11 square, 12 square, up to 31 square. All right, therefore, there are 22 numbers. 22 numbers have odd number of factors. Therefore, if you want how many numbers, 3-digit numbers have even number of factors. How many of them even number of factors? 900 minus 22. All right, therefore, it is nothing but 878. All right, now that becomes your response. All right, pretty simple question. You just have to know the concept that what kind of numbers have odd number of factors, what kind of numbers have even number of factors. Let's go further. Let's go quickly further into the study. I guess everybody's clear here. Right, I gave the reflection time. You might have done this. 3-digit number can be a question at our ability kind of 3-digit number or a 4-digit number, but you know how to figure them out. Okay, second important thing. Now listen to me very carefully. Here. So let's understand this. Now look at 72. All right, let's take a look at this. Let's take an example as 72. I want to count 72 has how many factors? Say that's a study. 72 has how many factors? Now listen carefully. So 72, I can list down all the factors. And I can say that 72 has 12 factors. I get 72 has 12 factors. You can list it down. So, but then how do you get this particular study? Listen carefully. I will show that concept once, but you will understand more of this kind of counting when you go to PNC. It's a counting. Number of factors, counting. Where do you actually get hang of counting? PNC. Therefore, there is a PNC here, there is a factor study coming here, and we put both of them and we make an algebra study at a later stage. Right now, there is a PNC study, but I'm refraining from that counting business. I don't want to now get into the fundamental principle of counting. I don't want to get there. Rather, let me just stay here. Let me stay here. Let me give a simple illustration as to how to count technically, or how to count in a very simplest manner, simplest possible way. So let's take a look at this 72. Now listen, first what you do on this 72 is, what do you do on this 72 is, first represent this as represent it as a function of primes. Represent this as a function of primes, which we did in one of the classes. Now what is 72? 2 raised to power 3, 2 raised to power 3, and 3 raised to power 2. What did I do? I resolved it into primes. I took 72. I found out which prime is coming how many times. So it's 2 raised to power 3 and 3 raised to power 2. So what does it mean here? It means to me that a 2 raised to power 0 divides 72, 2 raised to power 1 divides, 2 raised to power 2 divides, 2 raised to power 3 divides, but not 2 raised to power 4. That's the meaning of this study. All right, that's the meaning of this study. 2 raised to power 0 divides, 2 raised to power 1 divides, 2 raised to power 3 divides, and 2 raised to power 4 divides. Right? Yeah. Coming to the 3, when you have 3 raised to power 2, which means what? 3 power 0 divides 72. The 3 power 1 divides 3 power 2, but 3 power 3 cannot divide, because the highest power of 3 which divides this 72 is nothing but 3 raised to power 2. Also, the combination divides. That's what you mean by fundamental principle of counting. What do you meant here? You meant that 4 numbers divide here, 4 numbers divide here, and here 3 numbers divide. Combination, fundamental principle, just count them. 4 into 3, 12. 4 into 3, 12. Hey, what is this 12? 72 has 12 factors. 72 has 12 factors. Let me represent with a simple algorithm here. Simple algorithm. Hey, why did you multiply that? I'll come to this. 2 power 0. Let us write this 2 power 1, 2 power 2, and 2 power 3. Combine this with, combine this with 3 power 0, 3 power 1, and 3 power 2. Merge it. Combine these two fellows. Right now, that's what you mean here. Combine these two fellows. Hey, what do you mean? You mean that, okay, this is 2 power 0, 1 into 1, 1. 2 power 0, friends. 2 power 0 is 1. 1 into this number. Call it 1 into this number, 3. Call it now 1 into this number, 9. Just multiply like that. Similarly, rows and columns multiply and fill that particular box. Rows and column multiply here, 2 and 1. Call it, therefore, it becomes 2. Hey, 2 and 3, which becomes 6. Right here, 2 and 9. Call it now, so which becomes 18. All right, which becomes 18. Likewise, write the next row as well. I'm just showing where this 12 is coming from. Therefore, you are saying that, okay, this is 4, 12, 36. Next one, 8, 24, 72. Now look at this. What did you get here? You are trying to say that, look, this has 4 rows. First row, second row, third row, 4 row. That is the 4 here. That is the 4 here, 4 rows. Say how many columns? First column, second column, third column. Therefore, 3 columns, 4 rows and 3 columns. Therefore, how many cells? 4 into 3, 12 cells. There are 4 rows, 3 columns, 3 columns. Therefore, how many cells? 12 cells. Now, each cell has a different factor. That's what you said here. Each cell has a different factor. Therefore, hereafter, let us generalize and remember, if a composite number n can be resolved into prime like this, prime 1 raised to power a, if it can be resolved into prime like this, or let prime 2 raised to power b, or let if it can be resolved like this. So what did you write your answer as? You looked at this a, you wrote this as a plus 1. You looked at this a and you wrote it as a plus 1. What do you mean? All right, now here, friends, 3. All right, you had a 3, but what did you write? You wrote a 4. You had a 3, but you wrote a 4. Why? Because there is a 0th power, first power, second power, and third power. Therefore, you increased it by 1. All right, similarly, hey, what is the power here? All right, the second prime, what is the power? 2. But did you write 2? No, you wrote one more. Therefore, 0, 1, and 2. Therefore, you wrote it as 3. All right, therefore, you write this as what? B plus 1. A plus 1 and B plus 1. These many cells will be there. Nothing but these are the total number of factors of n. All right, not a function of n. Read it as factors of n. This is just a representation. Okay, it's not necessarily it's a standard of representation. Just for whatever I'm telling you, I'm just representing it as f of n. You don't have to write it as a function of n, right? It's not a function. The number of factors of n is a plus 1 and b plus 1. Hey, can I extend this study to 3 as well? Of course, yes. Already, therefore, if you have a number n, if it is written as prime 1 raised to power 1, if it can be resolved as prime 2 raised to power b and prime 3 raised to power c, therefore, what is the total number of factors of this particular number? Factors of this particular number: a plus 1, b plus 1, and c plus 1. B plus 1 and c plus 1. Right now, this becomes the factors of the number. All right, remember this, quickly remember this. All right, remember this. All right, if the number can be written as prime 1 raised to power a, prime 2 raised to power b, and prime 3 raised to power 3, c, all right, factors of the number is given by a plus 1, b plus 1, c plus 1. See, when you go to the permutation combination, once you're clear with the counting algorithm, this comes pretty naturally. There is nothing to remember. It naturally comes as a plus 1, b plus 1, c plus 1. But till then, just hang on. All right, till then, you just hang on. Remember this, pretty easy to remember. No big deal about this. All right, no big deal, pretty easy to remember. Fine, let's carry on to the examples. All right, here we go. Let's carry on to the examples. Okay, I resolved it. Given number 2 raised to power 4, 3 raised to power 3, and 5 raised to power 2. We already resolved it into prime. Ready? The components are ready. 4 questions given there. I'll give you 2 minutes. Components are ready. All right, 4 questions given there. I will give you 2 minutes. Answer a couple of questions. Possible, right? At least the first one is possible with everybody. First one is possible, and then push your pencil for the second one as well for a while. Push your pencil for the second one as well. Try that, quickly try that. Everybody, quickly try that. Well guys, here we go. Let's do it together. Let's do this. N is written as 2 power 4, 3 power 3 and 5 power 2. That's what he said. Find the number of factors of n. Total number of factors of n. Consider the complete sample size. Alright, therefore you consider the complete sample size. What is it? 2 power 4, 3 power 3 and 5 power 2. We know that okay, it is the function of these powers. This is your n. Therefore, what are the total number of factors? Number of factors is that 4 becomes 5, a plus 1. You look at this 3, 3 becomes 3 plus 1, 2 becomes 2 plus 1, which is this. Right? Therefore, you say that man, there are totally 60 factors. Great. Number of factors of the given number is 60. All right, yeah. Then he's saying that, hey, tell me the number of odd factors. Now listen, odd factors is a function of only odd numbers. Odd factors is a function of odd number. You can't, you see, basically, take the cards and design it like this. Take the 4 cards and put 2s on those particular cards. It's a card, friend. Card. I'm writing 2 on 4 cards. These are cards. I have a circular cards. I have cards on that I printed 4. Why did you print 4? Why didn't you print more? Because the question says print 4. I'll let 4 of them. Then I printed 3 on 3 of the cards. 3 on 3 of the cards. And I printed 5 on 2 of the cards. Now this is my cards. These are my cards. I printed these particular cards. Now look at that. When I say, now I always have a card as 1. I always have one card called as 1. You may say that, hey, why you will always have 1 as the card? Because 1 is a factor, which is 1 is a factor of every single number. Therefore, 1 is there. Whether you give, assume that these cards are with you now. These cards are with you. Now product of all these cards is the given number. Product is of these factors is the given number. So factors of this. Now when I want the odd factors, I said that okay, now this is the number. Now this is the number here. This is the number which you broken down into primes. 2, 2, 2, 2. Then you have triple threes, then you have double fives. So you've broken it down. I said that hey, you give me the cards, I will multiply so that the factor should become an odd factor. The factor should become an odd factor. You have to use these cards, because if you use another card, hey, I have another card 7 I will use, hey, then it will not divide the given number, friends. Then it will not become the factor of this. You have to use the existing cards only. You can't use more than this, but you can use less than this. You can give a part of this, but can I use more number of 3s than what is available? Of course not, right? Yeah. So therefore you are looking at these cards. So now you say that hey, give me the odd. So you say that you gave me only 3, let us say. You gave me one card of 3, no problem. All right, now therefore the 3 is the factor. All right, 3 is the factor. Next time you said that hey, I will give you 1 3 and 1 5. Absolutely no problem. 15 is the factor. Hey, what if I give only 1 5? If you give only one card on which 5 is written, 5 is the factor. Hey, what if I give 2 cards on which 3s are written? Then 9 is the factor. Fantastic. But can I give a 3 and a 2? I'll give a 3 and a 2. Not acceptable, because I said that odd number of factors, not acceptable. So therefore what you are trying to say, okay, although I have 2s, I can't use this row now. I can't use these 4 cards. If you can't use these 4 cards, the sample size is shrinking. What you are talking about the sample size now? I now can use only 3 power 3. 3 cards on which 2 is printed I can use. 3 is printed I can use. And then 2 cards on which 5 is printed I can use. I can't use these cards. Technically you are trying to say that I can't use them now. I can't use them. Fair enough. You can't use. Because the question is saying I have given the total number of cards. The sample size is defined. Figure out what is required for the question. If everything is required, use all of them and tell me what is the total counting. A part of it is required, use only a part of it and figure out what is the answer. Therefore, you would say that, okay, from here, 4 cards here. Let now to 3 raised to power 3 becomes 4. 5 raised to power 2, 2 plus 1, 3. What is 4 into 3? 12. Therefore, you are saying that, man, out of this 60, 12 of them have odd number of factors. So naturally, remaining 48 of them will have even number of factors. Naturally, remaining 48 would have even number of factors. Why? The given factor should be either odd or even. What is in between them? There is nothing in between them. Either it should be odd or it should be even. Okay, now assume that, hey, to find the even, is that the way to do it? Total minus odd gives me even. Not necessarily. It need not be necessarily dealt like that. Is there an alternate route to this? Let's find out the alternate. Now let's see that what is the direct way of dealing with this. Now this time you may say that, look, every time I don't want to give a 2 and something. See, you can't give me only 3. Along with the 3, you should give me a 2, because this time I need an even factor. 2 must be there in every card, in every set of card. Hey, can I give only 2 to you? You can give me only 2. There is no problem. Can I give 2 2s to you? No problem, because you have 4 2s you can give me. But can I give only a 3 to you? No. You have to attach this with a 2. Otherwise, I will not accept only 3. Therefore, what you will do? You will say that, hey, you keep 2 with you. You will say that, man, you keep 2 with you. I'll leave one card of 2 with you permanently. Assume that this card I will give you, because I don't want to give every time a 2. Keep that 2 with you. Now what I do inside is, therefore I'm left with 3 cards of 2 here, 3 cards of 2. I will permute this to 3 cards of 2, and then 3 cards on which 3 is printed. I have 2 cards on which 5 is printed. 5 is printed. What about this card outside? Nothing. It is there with you till the time this particular problem, third problem, gets over. Why? Because I gave already 2. Even if I give a 3 now, it becomes 2 into 3. If I give a only 5 now, it becomes 2 into 5. Therefore, what? This is one way, because you are not going to take it back till the time the third problem gets over. There are 4 problems. Till the time the third problem gets over, you are not going to take this back. Therefore, you write it as 1. Fair enough. Now, what about this 3? This becomes 4. All right, 3 becomes 4. Okay, what about this 3? All right, now 3 plus 1, which becomes 4. Hey, what about this 2? Becomes 3. All right, becomes 3. Now take the product of this. All right, 4 into 4 into 3. All right, now that is nothing but 48. That is how you got this. All right, that is how you got this. Hey, was all right, no, so will this now help in question number 4? Of course, yes. Think about it. Question number 4. Think about it. Question number 4. Number of factors of n which are divisible by 6. Divisible by 6 means what? Keep a 6 outside. Why? Because even factors means what? Divisible by 2. Divisible by 2. What did you do now? Divisible by 2. If it is divisible by 2, what did we do? All right, we kept it 2 outside. What did we do? We kept it 2 outside. Similarly, when I say that divisible by 6, the factor should be divisible by 6. Look, all right, now what are the factors? 6 divides this number, the given number here. Does the 6 divide? Of course, x. Does the 12 divide this number? Of course, yes. 12 also divides this number. Does 18 divide this number? Yes. Now, don't write the tables of 18. I'm not advising you the tables of 18 here. What I meant is, yes, there are these numbers which divide the given number, but how many? So now these are the kind of factors I want to list. I don't want you to list 2 as the factor. I don't want to list 3 as the factor. I don't want to write 9 as the factor. Those numbers are not required. Only the factors which are divisible by 6 are required. It should be a factor of n, but at the same time that factor should be divisible by 6. What I should do? Keep a 6 outside. Just like you kept a 2 earlier. Why? Because you wanted even. Even means what? Divisible by 2. Right? Divisible by 2. Similarly, divisible by 6 means keep 6 outside. But I don't have a card on which 6 is printed. Take a look at your cards. Right? Do you have a 6 printed on something? No. Therefore, what do? Take a 2. Keep a 2 out and keep a 3 out. Keep a 2 and a 3 out. Alright, you keep 1 2 and 1 3 out. Rest of the things you consider. Rest of the underlined things you consider. Therefore, what you are saying? I'll keep a 2 out. I will keep 1 3 out. I will keep 1 2 and 1 3 outside. So what about the rest of them? 2 raised to power 3. Alright, 2 raised to power 3. Here, friends, 2 raised to power 3. This you can write. Then 3 raised to power 2, because this is what you can permute now. 3 raised to power 2 and 5 raised to power 2. Now, what is this? You are not going to take it back till the time the fourth problem gets over. Therefore, this is one way. One way means what? Two ways means what? Giving it or taking it back. You are not going to take back either. You are not going to take back either of the cards. You are going to leave it there, because I am looking for factors which are divisible by 6. Therefore, you keep that 1. So, what about this 3? Becomes 4. 3 plus 1. 2 plus 1. And this becomes 2 plus 1. Right? Therefore, you say that, okay, this is nothing but 36. There are 36 factors out of total of 60 factors. There are 36 of them which are divisible by 6. Right? Which are divisible by 6. Simple problem. You just have to understand how this factor counting happens there. Right? It need not be total every time. The first question is about total. It need not be total every time. It can be restrictive. As you go along, they restrict. They'll say that, hey, give me only odd, tell me only even, tell me which are divisible by 6. It can be restrictive in nature. Right? The idea is they can get restrictive in nature. Right, great. All right, let's go further. Let's go further. Let's go further. Right, okay, now let's come to this point. Factors. Express the given number as a product of two factors. Again, all right, now how do you do it for a non-perfect square number? How do you do it for a perfect square number? Two things. All right, now we need to divide them into two things to start with. Non-perfect square number and a perfect square number. Let me take one of the non-perfect square number, 72. We are very familiar now. All right, 72 is a pretty familiar number. Let us start with 72. Let's start with 72. Let me list down all the factors which are less than root 72. Friend, what's the root? It's a root 72. Root 72 is 8.x. 8.x. What is the approximation of root 72 is another class lecture. Not in this class, it's another class lecture. We'll go there later. Alright, it is 8.x. Alright, because it lies between 8 and 9. So alright, therefore think up to 8 clearly. 1 divides, 2 divides, 3 divides, 4 divides, 5 does not, 6 divides, 7 does not, 8. Right? All right. Now, because we had 12 factors, I'm listing down all the 12 factors now. All the 12 factors now. Pretty simple, friends. 1 into 72 is 72. Because once you listed one side, other side listing is easier. Hey, what do you mean by once you listed one side? You listed all the numbers which are less than root 72. There will be equal number of numbers greater than root 72, which means there will be equal number of numbers greater than 8. And how do I write it? Simple. Wallet now 1 into 72 is 72. 2 into something is 72, 36. 3 into something is 72, 24. 4 into something is 72. Well, no, that's nothing but 18. 6 into something is 72, 12. 8 into something is 72, 9. Now look at this. What did I do here? There are 12 factors. In fact, these were the 12 factors of the number 1, 2. These are the factors. Well, these are the factors. 1 is a factor, 2, 3, 4, 6, 8, 9, 12 are numbers. What did I do? I made a logical pair. I made a proper pair so that I wrote it as a product of two factors. I wrote 72 as a product of two factors precisely. All right, all these are the factors. It has 12 factors. Did I write it as a product of two factors? Yes, I did not borrow anything from outside. All these are the product of factors. Therefore, how do you write this? Therefore, the number of ways of writing it as a product of two factors. Given a number which is not a perfect square. If it is not a perfect square, it will have even number of factors. It will have even number of factors. Even number of factors, right? It will have even number of factors. It would have even number of factors. Right, even number of facts means factors, even number of factors. How do you write it as a product of two factors, guys? Here f1 and f2 are not different. I'm just representing it. How do you write n as f1 into f2? There is no order. Now don't say that 1 into 72 is different from 72 into 1. No, I didn't mean that. It's just a product of two factors. That's it. Now which is the order does not matter. F1 should be less than f2 should be greater than f1. There is no order to it. I'm just saying representation of a thought, mathematical way of expressing this thought, right? Yeah, f1 and f2, all right, now writing it as a product of two factors is nothing but factors of the number divided by 2. We already learned how to find the factors of the number. So which means if I say that a number of ways of writing 72 as a product of two factors, factors of 72 divided by 2. Why divided by 2? Because I'm making pairs. I'm not making triplets. If it is triplets, divide by 3. I'm writing it as the pairs here. Therefore, factors of 72 divided by 2. All right, so factors of 72, how many? 12 divided by 2. How do I know it is 12? We did that problem all right, earlier also. Here also I listed all the 12 factors. 12 by 2, therefore you say that 6 ways. All right, 6 ways. Therefore there are 6 ways to write this. Point number 1. Let's take point number 2. Let's take a point number 2 here. Second point. Hey, what if it is a perfect square? Because if it's a non-perfect square, it would have even number of factors. Division by 2 is simple. Perfect. All right, now what if it is a perfect square? Let's understand. What if it is a perfect square? Let's understand it here. 36. Take an example as 36. It has 9 factors, right? It has 9 factors. Hey, what is root 36? Root 36 is 6. Let root 36 is 6. Right, up to 6 here. Let's write it up to 6. What are the numbers divide? 1 divides, 2 divides, 3 divides, 4 divides, 5 does not divide, and 6 divides. Perfect. Okay, write the other side of the pair, other side of the number. 1 into 36. Great. 2 into something, I'm writing the other side. In fact, these are the factors, friend. 36 is a factor. 2 into something, 2 into 18. 3 into something, 12. 4 into something, 9. All these are 36. Now we said, hey, 6 into 6. But the point is you cannot write the same factor 2 times. You cannot write the same factor 2 times, only one factor, which means now you are saying that 6 does not have a company. There is no pairing available for 6. There is no pairing. There is a pairing available for 1, pairing available for 2, 3 has a pair, 4 has a pair, 6 does not have a pair. Can I write once more? You should not. Technically, you should not. 36 has 9 factors. It's a perfect square. It has 9 factors. Therefore, 36, now the point comes here. Product of any two factors whenever it's a perfect square. If n is a perfect square, n when it is a perfect square, if it is a perfect square, it would have odd number of factors. It would have odd number of factors. Alright, it would have odd number of factors. If it has odd number of factors, now two cases come. Therefore, write n is equal to f1 into f2, where f1 is different from f2. F1 and F2 are distinct numbers, which means product of two distinct numbers. All right, the word comes here, product of two distinct numbers. Or you can also write this as product of, all right, now product of any two numbers, which means can F1 also be equal to F2? Can F1 also be equal to F2? Yes. All right, you got to watch for the words in the question now. Any two factors. How do I do that in this case? All right, now in the first case, you will say that the answer is going to be 4. All right, 4 distinct here. First case, answer is going to be 4. Right. In the second case, what you also do is in the second case, you add a dummy into 6. You will add this here. Into 6 into 6. Therefore, the answer becomes 5. Any two factors, because F1 can be equal to F2. Use factors, but don't use anything from outside. But the duplication of factor will be available because the word used is any two factors. Okay, how do I summarize this? Factors of the number. Therefore, you will say that factors of the number minus 1 divided by 2. Why did I do minus 1 earlier? Because this 6 was not having a pair. All right, because I said that it should be product of two distinct factors. Therefore, you will say that, hey, this fellow does not have a pair. Remove it and then divide, because it has 9 factors. If you do 9 by 2, it becomes 4.5. Hey, there is nothing like 4.5. Either tell 4 or you tell 5. Distinct factors, then tell 4. Reduce it and do it. Hey, what about any two factors? Product of any two factors? Then you can write the first one and the second second one to be same. Possible. This is also one of the cases possible. In that case, what you do? Factors of the number plus 1 divided by 2. That is 9 plus 1, 10 divided by 2. Answer would have become 5. You need to be little careful when it comes to the perfect square. You need to be little careful there. All right, you need to be just as notch little careful there. Right, you need to be little careful there. Okay, let's go further, friends. Let's go further. Another point here. Hey, what if the product of two co-prime numbers? Sometimes it comes in. All right, no, that also comes while we are doing the applications in algebra. Third point, we looked at it when it is not a perfect square, how to do it. We looked at when it is a perfect square, we checked how to do it. Hey, whether it is a perfect square or not a perfect square, how to write it as a product of two co-prime numbers. We'll take a look at the same example 72 here. Take a look at the same example 72 here. Product of two co-prime numbers that I am writing. Are 1 and 72 co-primes to each other? Yes. Or 1 and 72 co-primes to each other? Yes, that is qualified. 2 and 36 not qualified because they are not co-primes. 2 and 36, 2 is the HCF. Because now I am asking that, man, please write it as a product of two co-prime numbers. Disqualified. 3 and 24 disqualified because 3 is the HCF. 4 and 18 disqualified because 2 is the HCF. 6 and 12 disqualified because 6 is the HCF. 8 and 9 qualified, which means had I asked the same question in how many ways 72 can be written as a product of two co-prime numbers, your answer from 6 ways would have been changed to 2 ways. Would have been changed to 2 ways. All it would have been changed to 2 ways. Hey, how it is becoming 2 ways? All right, how do I do that? Now look, listen carefully. If the number can be written as prime 1 raised to power a and prime 2 raised to power b, right? Number of ways of writing n as the product of two co-prime factors, f1 and f2, where the f1 and f2 are co-primes to each other. They are co-primes to each other, co-prime factors, not any factors. F1 and F2 should be co-prime. That is written, that is given by, that is given by total number. Number of ways of writing this is given by F, is nothing but 2 raised to power number of prime factors divided by 2. Number of prime factors divided by 2. This is something that you may have to just remember. Number of, again, when you go to PNC, this concept would be clear. It becomes clear, but I don't now want to digress into PNC here, right? Number of ways of writing this becomes 2 raised to power number of prime factors divided by 2. Go to 72, friends. Let's go to 72. Hey, what was this, man? 72 is nothing but 2 raised to power 3 and 3 raised to power 2. How many prime factors are there? Only 2 prime factors. 2 is one of the prime factors and 3 is one of the prime factors. Of course, 72 has 12 factors, but how many prime factors it has? Only 2. It has only 2 prime factors. It has only 2 prime factors. Therefore, what is that we are trying to say? Or we are saying that the number of ways of writing this 72 as a product of 2 co-prime factors. As a product of 2 co-prime factors, write it as F1 and F2. Or where write this 72 as F1 into F2, where F1 and F2 are co-primes. Where F1 and F2 are co-primes. That is written as, that can be written as number primes. 2 raised to power 2. This 2 raised to power number of prime factors, that is 2 divided by 2. That is 4 divided by 2. 2. Therefore, 2 ways. Therefore, 2 ways. Let me give one quick example. Let's take another example. What if my number? What if my number is 2 raised to power 1, 3 raised to power 1, 5 raised to power 2, and 7 raised to power 1, 5 raised to power 2, and 7 raised to power 2. Now, how many ways you can write this n as a product of 2 co-prime factors? Simple. Now 2 co-prime factors. You would write this as 2 raised to power. How many prime factors? 2 is prime, 3 is prime, 5 is prime, 7 is prime. 2 raised to power 4 divided by 2. What is 2 raised to power 4? 16. What is 16 divided by 2? 8. Therefore, you would say that 8 ways. I guess 3 points I made here. 3 points I made here. Writing or not a perfect square. If the n is not a perfect square, n is not a perfect square, writing this as a product of 2 factors is given by number of factors of n divided by 2. Point number 1. Well, that's the first point that we made. Second point, if n is a perfect square, if n is a perfect square, writing it as a product of 2 factors. Now either it will be number of factors minus 1 by 2, or it will be number of factors plus 1 by 2. Point number 2. Point number 3, writing the given number as a product of 2 co-prime factors. Writing it as a product of 2 co-prime factors is nothing but 2 raised to power p by 2. 3 things. We'll talk about 3 things. All 3 things are applicable in a big scale as we go on to the algebra. Therefore, now, so this is keeping the vision. you have to keep the future in mind while you are learning certain concept, because it is not about isolation. It has to dovetail. It has to dovetail. You have to connect the concepts at some stage. Therefore, you know that some concepts are very important because they have the future application, scalable applications. Everything is not scalable. Everything does not have a scalable. I generally pay more attention to the ones which are scalable. I will keep telling them. Whichever are the scalable ones, I'll keep telling them in the class. You need to pay special attention and you need to master them clearly there. Right, great. All right, now that's about it. That's about then. Third point, sum of the factors of the number. Sum of the factors of the number. All right, let's take a look at the sum of the factors of the number. Here we go. Sum of the factors of the number. What did you do? Take the same number 72. Take the same number 72 as an example. How many factors it has? 12. Now this time I'm saying that, hey, why don't you add all these factors? All right, why don't you add all these factors? What do you mean? 72 is 2 raised to power 3 and 3 raised to power 2. Hey, what were the factors of this particular number? 1 was a factor, 2 is a factor. All right, now these are the factors 1, 2, 3, 4, right? Then we had 6 as a factor, 8 as a factor, 9 as a factor, 12 is a factor, right? And then we had 18 as a factor, then we had 36 as a factor, then 72 as a factor. So the 24, 18, 24, 36 and 72. These are the sum of these 12 numbers. Technically these were the 12 factors 72 had. This is what I wanted. Sum of the factors means this is what I want. Let me write it like this: sum of factors of 72. Just a representation, friends. Representation. You want to represent in your own style, absolutely no problem. I'm just, whatever I'm talking, I need to connect with you. All right, therefore I'm writing it as sum of the factors of 72. It is not any standard textbook notation or something. I'm just representing it in a simplistic fashion so that you kind of connect with me. Sum of the factors of 72 is nothing but this. Hey, how do I get this? All right, 72 is fine, 12 factors. What if a number has some 30, 40 factors? Of course, large numbers have it. Just like we took one example, it had 60 factors. Is it possible to sit and count those 60 factors? No, that's not the way we are advising you to do. So how do I get this? It's a GP. Undercurrent for this is GP. Hey, what is this concept? This concept is GP. Now look at this. You had 2 power 3. You had this 2 power 3. Take this 2 power 3. You'll be writing this as 2 power 0, 2 power 1, 2 power 2 and 2 power 3. Now these are the GP. This is the GP. This is one GP. First GP whose common ratio is 2. Perfect. All right, whose common ratio is 2. Now this is the second GP. All right, second GP. All right, now so what is that? Look at 3 power 2. Write as 3 power 0, 3 power 1 and 3 power 2. All right, it is 3 power 2. This is the second GP. All right, second GP whose common ratio is 3. All right, whose common ratio is 3. Now those who are not comfortable with GP etc., don't bother. Now don't bother. Now what I'm doing here, I just have to, all right, now let's say that, hey, are these numbers coming by writing like this? Let's check, friends. Let's check. 2 power 0 with this, all right, you got it as 1. 2 power 0 with this number, all right, you got it as 3. 2 power 0 with this particular number, you got it as 9. Perfect. All right, now that's one side of the story. All right, now let's start with 2 power 1 now. Let's start the story with 2 power 1. 2 power 1 with this, right? Now that has become 2. All right, 2 power 1 with this. All right, now that has become 6. All right, 2 power 1 with this next number, all right, which has become 18. Now look, you are getting them 1, 3, 9. There is 1 here, 3 here, and 9 here. Similarly, next 2, 6, 8. All right, now there is a 2 here, there is a 6 here, there is a 8 here. Likewise, when you start next ones, all right, you will get all the numbers. Therefore, what? Sum up to n terms of this particular GP series. How do I write, friends? How do I write 4 terms of this particular series? You write this as 2 raised to power 4 minus 1 divided by 2 minus 1. That's how you write. All right, now GP up to n terms of the series. How do you write? All right, now a r raised to power n minus a, all right, minus a divided by r minus 1. This is how you write sum up to n terms of the GP, whose first term is a and the common ratio is r. Whose first term is a and the common ratio is r. This is what we do. All right, this is what we do. Now don't bother. When we go to the progressions chapter, this will be digested better. But yeah, sum up to n terms of the GP, whose first term is a. All right, generally, how do you write a GP series? First term is a, second term ar, third term ar square. Likewise, what is the nth term? Nth term is ar raised to power n minus 1. All right, this is the first term. All right, this is going to be the first term of the GP. This is the second term. This is the third term. This is the nth term. So how do you find the sum of these particular terms? Therefore, if I put a plus, how do you write the sum of these particular terms? Is nothing but this. This is the sum of the n terms of the GP, which you learned in the schools, all right, which you learned in the high school, right? That's what you learned. Now this is what I'm going to use it here. Hey, how I'm going to use it here? This I used it already here. I used it. Similarly, I'm going to use it on this as well. This becomes 3 raised to power 2, 3 raised to power 3 minus 1 divided by 3 minus 1. Let's write the general form. Just say the general form. Even if you didn't connect with this much, does not matter. At least by heart this. At least by heart this. All right, till the time we go to progressions, by heart this. When we go to progressions, this comes very naturally. All right, whatever you are by hearting with some effort now, you will realize at that point in time that this comes pretty naturally now. Right now, today you are by hearting it. After some time, it comes pretty naturally. Let's understand this. Therefore, if my number is written as prime 1 raised to power a, just like here this was prime 1 raised to power a 2 power 3, right? Prime 2 raised to power b, all right, which is 3 power 2, all right, prime 2 raised to power 2. So how do you write it? Sum of the factors of this number, sum of the factors of the number. Simple, friends. Look at this part, look at this part, write it as prime 1 raised to power a plus 1 minus 1 divided by prime 1 minus 1. You got to write it like this. Okay, what about the second one? All right, for this second one, all right, for this one, prime 2 raised to power b, write it as prime 2 raised to power b plus 1, prime 2 raised to power b plus 1 minus 1 divided by prime 2 minus 1. Well, what is the undercurrent? Undercurrent is sum of n terms of the GP. That's undercurrent. Undercurrent is this. Hey, what if there is a prime 2 prime 3 raised to power c? Write one more. If there is a prime 3 raised to power c, say into a I had another prime 3 raised to power c, no problem, write one more here. Well, let write that also. Therefore you will write prime 3 raised to power c plus 1 minus 1 divided by prime 3 minus 1. All right, prime 3 minus 1. I leave the hint. Hint is nothing but the GP, sum up to n terms of the GP. All right, that's going to be the hint out there. All right, that's going to be the hint. Okay, let's take a look at the question. Some of the simple questions on this. Remember this. Remember this portion. I want you to clearly remember this portion right now. All right, remember this portion. Let's quickly do the application before we move to the remainders. Let's look at the applications. Couple of applications. We look at it. Okay, I'll give a minute. Write the first one. Make an effort. Write the first one. Note down this formula somewhere. Note it down right now. Note it down. Note it down. Yeah, apply it here. Apply it here. I'll give a minute or two. Apply it in a couple of questions. You already know how to deal with them. Apply it. Yes, guys, let's take a look here. Let's take a look. Some of the factors. Well, it is talking about some of the factors of this number. Some of the factors. The first one, all the numbers you all entire number you got to take 2 power 4. You have to understand the sample size. That's very important here. 5 power 2 complete sample size, which comes from the factors. Therefore you look at the first one. All right, therefore this is 2 raised to power 5 minus 1 2 minus 1. You look at this, you write it as 3 raised to power 4 minus 1 3 minus 1. Then you look at this is 5 raised to power 3 minus 1 5 minus 1. Right, this is what you kind of write. Now simplification is simple. You will write that this is 31 by 1, 31 by 1 3, that is 80 divided by 2. Right, the next one alert, which is 124 divided by 4. We can simplify this. That's not a challenge is not that. If I can write this line, if I can write this, then the simplification is never a problem. All right, let's take a look at the second one. Odd factors. Sum of odd factors of this particular number. Odd factors means what? As we said earlier, 2 power 4 does not play a role. 2 power 4 has no role to play there. So therefore you would say that therefore it has 3 raised to power 4, 3 raised to power 3 into 5 raised to power 2. Now this has a role to play. 2 power 4 has no role to play. So you look at this and you write this as 3 raised to power 4 minus 1 3 minus 1. This is the sum of the factors generated by 3 power 3 and 5 power 2. These are the sum of the factors generated by this. 5 power 3 minus 1 divided by 5 minus 1. We'll simplify this, which becomes the answer. Look at the next one, third one. Look at the third one, sum of the factors of the number. How did you find while finding the factors? You said that keep a 2 with you, or that's what you said, keep a 2 there, that's what you said. Then inside the bracket you wrote it as 2 power 3, because even factors, even means what? Keep a 2 outside. To keep a 2 outside, you had a 2 raised to power 4. Out of 2 raised to power 4, you kept it 2 outside. Therefore, what is inside the bracket now? Active bracket. 2 raised to power 3, 3 raised to power 2, and 5 raised to power 2. That's an active bracket. Great. Now look at the active bracket and write the elements. This is 2 raised to power 4 minus 1, 2 minus 1. Right here, 3 raised to power 3 minus 1, 3 minus 1. Likewise, 5 raised to power 3 minus 1, 5 minus 1. Write this particular portion right now, but then here this 2 is not crossed just like before. Now if you look earlier, what did I do? I crossed it off because it has no role to play, but here I did not cross it, I kept it outside. Therefore, what? Bring this. While counting it was not required, but while taking the sum it is required. Why? Because every factor you made it double. That's the reason you said that keep this 2 outside with you. Therefore, whatever the number that you get from here, you got to double it. All right, it is not that this 2 is not having any role here. The 2 does have a role to play. Right, this 2 all does have a role to play. All right, yeah, I guess all right, now the things are clear to you. Now that's the story between the sum of the factors of the numbers. All right, now we'll go to the remainders. Oh, there is a lot that you can study from here. There is a lot, but I gave the fundamentals clear to you. I made the fundamentals very clear, how to count the factors, how to express the factors as the product of two numbers, how to sum these particular factors. Yeah, if you want, I'll quickly take one example built on this. Now take a look at this. Let's take a look at this. Find the sum of the perimeters of all possible rectangles. Perimeters, the word is perimeter. Find the sum of the perimeters of all possible rectangles whose area is 240 centimeters squares and sides are integers. Of course, the integers can be negative, but the point here is because it's a sides of this rectangle, it's a side of a rectangle, it has to be a positive integer. Although the word positive is not there, it is understood because you cannot make the side of a rectangle as negative. Already it has to be positive. Now look at this particular question. What do you mean? The area is 240. Already area is 240 centimeters square. What is the meaning of this? It means this. Alright, now can I write the area length into breadth? Can I write the area as 240 into 1? Of course, yes, you can write as 241 into 1. Hey, can I write it as 120 into 2 length and breadth? That's right. Already you can write it like this. So now what are these now? Now can I write this as 80 into 3? 80 into 3, yes, already you can keep writing. This is what one way, this is the second way, this is the third way. Now this is what you are writing here. Already this is what you are writing, this 240 as them. Now what are these here? 1 is a factor, 2 is a factor, 3 is a factor, 240 is a factor, 120 is a factor, 80 is a factor. What you should be doing? 2 times of length plus breadth. Alright, that is the perimeter. Perimeter is nothing but what? Perimeter of a rectangle. 2 times of length plus breadth. That's what you are supposed to be doing. Great. So nothing but what? What is length plus breadth? Factors. Alright, these are the factors. 1 is a factor. 240 is the corresponding factor, which area becomes 240. 2 is a factor, 120 is a factor. Therefore, what is that I'm supposed to be doing? Add up all the factors, but just be mindful to double this. Or let's just be mindful to double this. Hey, why mindful to be double to this? Because it's a perimeter. Or let's see, when I write a construct, all right, now this rectangle 80 by 30, 80 by 3 might look something like this. This can be 80 by 3. Well, at 80 by 3, but the point here is what? There is another 80 perimeter, there is another 3, therefore double the numbers. All right, double those particular numbers. Double what? Therefore the factors. Therefore what you are trying to say? What is the answer to this question? Sum of the factors of 240. Sum of the factors of 240 double. Sum of the factors of 240 double. That becomes my answer. Sum of the factors of 240. That is nothing but the edge and nothing but the length and breadth of the rectangle. So, but you got to double it because it's a perimeter. 3 has to be duplicated. 80 has to be repeated. Right now, that's what you kind of do there. So therefore, you will say that okay, 240. What is this 240? Split it. We already learned how to split this particular one. Split this part. Right. Therefore, you will say that 2 raised to power 4. That is 16. Let 16 into 3 raised to power 1 into 5 raised to power 1. Right, into 3 raised to power 1 and 5 raised to power 1. That is what you split it as. Therefore, you write it from here. 2 raised to power 4 becomes 2 power 5 minus 1, 2 minus 1. Right, similarly for 3, 3 square minus 1, 3 minus 1. Right here, 5 square minus 1, 5 minus 1. Okay, now do what? Double it because author said that you got to double. Perimeter is required, therefore double. Okay, simple. Like this, some application will be created. Already, question need not be very bland the way I projected it. Find the sum of the factors of this number. It need not be that bland, right? Watch out for the scenario. Word problems we call it. They have to bring in some words. At times it can be bland. At times it can be pretty bland, no doubt. But sometimes they add words. That's a nicer way. See, addition problem that you did in class one. Alright, class one when you do the addition problem, there are word problems at the end of every chapter. Of course, first you learn addition. What is 23 plus 7? Of course you learn. But then after that, already you learn little more. Already you add words to this. Already you have 23 chocolates, and already your parent gives another 7 chocolates. Therefore, how many chocolates you have? Now it is what you give it 7. Child has to understand that I have to add these chocolates. Word problem. Pretty similar to this. Whatever the concept I'm discussing in raw, or it can they can put some words to this. It's not very it's not very difficult to understand them. You just need a little bit of exposure to understand them, right? You just need some exposure to understand. Great. All right. Now here we go. Let's go to the study further. Let's go to the study remainders. Let's take a look at remainders for the next 40 minutes or so. We'll try and do some of the remainders. Properties, friends, even before we do the properties, please watch out the numbers two video in case you have not done that. Please watch out. There I took a lot of examples on these properties as well in the numbers two. So here I'm just did the division. Basically, where is it coming from? Division. Basically division algorithm. Remainder is a function of division, of course. We discussed quite a bit of this. Now my representation for this class, let me summarize those some are 3 or 4 properties and move on. So okay, if I have numbers here, number 1 plus number 2 and number 3, let's say that okay, I have to add 3 numbers and divide this by a particular divisor and give me the remainder. It's not numerator denominator, it's a divisor. What it says, what it is, I have a divisor. I am supposed to be adding number 1, number 2 and number 3. Of course there is some quotient here, but I'm interested in remainder. So one thing you are not interested in the remainder problems is quotient. What you are interested in, divisor you are interested in, numbers you are interested in, and remainders you are interested in. You are not interested in quotient. Sometimes that's very important to know. Otherwise sometimes you bother about the quotient. Quotient is not important. Divisor is important. Numbers are important. Which number you should divide is important. Therefore, what is the remainder? That is important, right? Yeah. So what we do? Isolation. For technique number 1, isolate and attack. Isolation. All right, we'll work in isolation. What do you mean? All right, I'll find the remainder when number 1 is divided by d. So first remainder. All right, a plus, because there is a plus here. This plus, I will repeat that plus. Number 2, I divide by d. I'll write the second remainder. Okay, number 3, I divide by d. I will write the third remainder. All right, now please watch out the numbers 2 video. All right, somewhere there I came across these concepts and I mentioned it. Isolate. All right, basically idea is what? Isolate and attack. Reason being, hey, why we are learning this? Reason being, see, you will have 23 raised to power 27, all it added to 29 raised to power 31, all it when divided by 7, what is the remainder? What is the remainder? Why cannot technically add these numbers? No way I can add these numbers. Add and then divide. I'm not going to do that. What I do, isolate and attack. Simply divide 23 raised to power 27 by 7. We'll find that out, or we'll find it out. How do we do this? We'll find that out. So divide and then get to the answer. That's a easier way to deal with this. All right, that's a better way to deal with this. You will not add. There is no way you are going to add. We need a supercomputer to add these numbers. We need supercomputer to add this. We don't add. What we do, isolate and attack. All right, that's a point here. Hey, what if there is a subtraction sign between any of the numbers? Don't bother. Add, subtract. If there is a subtract, you subtract. Hey, what if there is a multiplication sign between them? Multiply. My point here is what? Isolate and attack. Isolate. All right, now don't accumulate, rather you isolate. All right, don't accumulate them. Isolation is the strategy there. Point number 1. All right, point number 1. Point number 2, given, I already said this to you. I already wrote these parts to you. Given, when a number is divided by a divisor, remainder is r. This is given. This is given. All right, now a couple of derivatives from here. Point number 1, we talked about it. When k times of the number is divided by the same divisor, the remainder is going to be k times of r. All right, remainder is going to be k times of r. Point number 1. Then we discuss another point. When number raised to power k is divided by the same divisor, answer will become remainder raised to power k. Whatever you do to the number, if you raise it to the power k, you better raise it to the power k. Raise it to the power k. We already talked about this in the previous video. Please preview, watch out that previous lecture, right? R raised to power k. That's a point number 2. Okay, point number 3, when k times of the number is divided by k times of the divisor, still your remainder becomes k times of r. Now some people don't conclude, oh, k and k I will cancel. No, you are not cancelling. It's a division. It is a division. It is not simplification. These are not these are not the numerator and denominator. It's a divisor. See, look at this. 6, I gave the number as 20. Man, you will not divide them. You will not divide, saying that okay, 2 3 times and then 2 10 times and now I'll do the problem. No, you are not going to do that in division. Alright, you are not going to do that in revision. Be mindful about it. Alright, therefore k and k does not get cancelled. If you multiply, alright, if there is a number given, number divided by divisor leaves r as the remainder. Hey, what if I do k times of the number by k times of divisor? Still you get k times of remainder. Still you get k times of remainder. Okay, these are the three results derived out of this. Given this, these are the three results that you should kind of remember. Another important property, preferred remainder. Watch out for the preferred remainder. These are the 3 points that you should remember. Point number one, isolate and attack. Point number two, given this, I can derive three important results there. Preferred remainder. What is the preferred remainder? Either 1 or -1. Well, keep your eyes and ears open, keep your all senses open to figure out whether I'm getting a preferred remainder, which is 1 or -1. Why I call them as the preferred remainder? See, what misses is the -1. 1 comes very naturally to you. That's not a problem. -1 does not come naturally, right? -1 does not come naturally. Therefore, I'm listing it down clearly saying that, man, it is a preferred remainder. Be little mindful about the preferred remainder. So what does it mean to us? All right, now let me say 1 raised to any power becomes 1. 1 raised to any power becomes 1. -1 raised to odd power. -1 raised to odd power. -1 raised to odd power becomes -1. -1 raised to even power. All it becomes 1. -1 raised per even power becomes 1. Therefore, 1 and -1 are pretty useful numbers, very friendly numbers. All it in remainder especially. All it in remainder especially. Okay, let's first put all it now this preferred remainder to practice. Let's put this preferred remainder to practice before we understand that the preferred remainders I'm not able to see. The moment you stop seeing the preferred remainder, then we will see how some of the theorems can help us. All right, how some of the theorems can help us. Okay, minute here, guys. Preferred remainder. I guess everybody can do this. All right, take a minute. Take a minute. I want you to run through this and quickly list out the preferred remainders for yourself. Take a minute and list out those numbers for yourself. Hmm. Okay, you might have listed it. Let's do this together. Let's do this. Find the remainder when 7 raised to power 36 is divided by 5. Simple. All it now list out 7 raised to power 1. 7. How do you think? All it now preferred remainder 7 power 5 1 divided by 5. The remainder is 2. Okay, then you will say that okay, 7 square divided by 5. Remainder is -1. Remainder is -1. That's what I meant by the preferred remainder. 7 square divided by 5. The remainder is -1. So how do I write 7 raised to power 36 here, friends? 7 raised to power 36. All right, the denominator is a divisor. I already told you. Numerator is a number, denominator is a divisor. It's not a numerator and denominator. What I wrote in the numerator is the number, which should be divided by the number in the denominator, which is a divisor. Yeah, how do I write 7 raised to power 36? 7 raised to power 36 is nothing but 7 square raised to power 18. That's what you are trying to say, 7 square raised to power 18. So therefore, you look at this now here. Now this is the number 7 square when divided by 5. The remainder is -1. All right, but 7 square raised to power 18 when divided by 5, the remainder will be -1 raised to power 18. Properties. We just talked about that property here. All right, we just talked about that property. It is based on this property here. All right, now the property number 2. All right, we talked about this property. All right, we talked about the property number 2. All right, that's a property we are talking about. This property. We just talked about this. Given this, All right, given n divided by d, divisor remainder is r, n raised to power k, remainder will become r raised to power k. Just you got to remember those tiny properties, very small ones. This is what we apply in the big numbers to do it. Minus 1 raised to power 18 is what? We said that minus 1 raised to power 18 is nothing but one preferred remainder. What was the preferred remainder? Minus 1. Just be mindful about the minus 1 because plus 1 comes very naturally to us. The minus 1 does not come. We make some small pattern till we get the preferred remainder. If we get the preferred remainder very early, good, no frustration, pretty good. All right, therefore you say that the answer here is nothing but my answer here is nothing but 1. All right, answer here is nothing but 1, right? Yeah, look at the second one, same question. All right, till here you reach till here. All right, you reach till here. Only from here the dynamics will change a little bit. So from here you will say that 7 raised to power 2 raised to power 14. All right, because it's 34. All right, raised to power 34. All right, 7 raised to power 14, right? Yeah, sorry, 17. All right, raised to power 17, all right, divided by 5. The remainder is going to be minus 1 raised to power 17. It becomes minus 1 raised to power 17, which is nothing but minus 1. But the point here is, can I write the answer as minus 1? No, that's not allowed. Remainder is not negative. What do I do? Add the divisor. Whenever you get the negative remainder, what you should be technically doing? Add the divisor. What was your divisor? 5. Add the divisor and write it as 4. That's therefore minus 1 we should not represent. Rather, we should be representing the answer as 4. All right, we should be representing answer as 4. All right, that's what you do when you get the negative remainder. Next one, 29 raised to power 530 when divided by 20. Now listen guys, take 129 first. I want you to do this. Take 129 first, divide this by 20. Divide this by 20, remainder is 9. All right, when number is divided by 20, remainder is 9. But the point here is, number raised to power 530, then remainder also gets raised to power 530. And then will this the answer? Of course no, because remainder has to be less than the number divisor. Remainder has to be less than the divisor. Therefore, what you should be doing? Divide by 20. Divide this by 20 because you can't list a remainder which is greater than the divisor, or a remainder greater than the divisor. Therefore, divide it. What is the property that you use? The first property. When now it's the same property that you used, or the same property that you used, what you used in the previous question. 9 raised to power 430, 9 raised, let's see. Again, let me do it once again here quickly. Take only one. Don't bother about this 530 for the time being. When a 29 is divided by 20, the remainder is 9. Remainder is 9. What you are trying to do? But you have 29 raised to power 530. If you put 530, then the remainder also should be raised to power 530. But is this greater than your divisor, which is 20? Of course yes. Therefore what you should be doing here, you should be dividing this by 20. Great. So 9 square is fine because 9 power 1 by 20, 9 is the remainder. 9 square is divided by 20, very convenient. 9 square divided by 21 is the remainder. 1 raised to power anything, 1 is the answer. Therefore answer is going to be 1 here. Simple. Okay, point here is what? If the number becomes like 29, if I don't know how to take the 29 square, etc., don't bother. First make the number smaller. First make the number smaller and then, all right, and then apply the property. Make the number smaller and then go to the squares and the cubes, etc. Right, that's a point number 1. All right, that's a point number 1. Second point, second one, let's take a look at this particular number here. Let's take a look at this particular number here. 2 raised to power 95 divided by 19. Let's say that I have this proposition where 2 raised to power 95 divided by 19. This may frustrate little bit. Well, this may frustrate little bit because I need to get the preferred remainder either as 1 or minus 1, right? So if I see this, a 2 raised to power 1 by 2, 2 raised to power 1 by 2, I got the remainder as 2 raised to power 1 by 19 because my divisor is 19. 19, remainder is 2. 2 raised to power 2 by 19. All right, the remainder is 4. All right, 2 raised to power 3 by 19. Right, the remainder, all right, now here has become 8. All right, 2 raised to power 4 by 19. All right, 2 raised to power 4 by 19. Remainder here is 16, or you can write it as minus 3. Minus 3 or 16 does not matter. Still, I am not getting the preferred remainder. A 2 raised to power 5 divided by 19. All right, now that is 32 divided by 19. Right, you will say that, okay, the 32, all right, 32, therefore you would say that that's going to be 13. It's still frustrating. Look, I'm not getting that minus 1 or minus 1 anywhere. That is when you say that it's better to know 1 or 2 small theorems. It's better to know 1 or 2 small theorems. Let's understand. So there is a Fermat's theorem. How does the Fermat's theorem work? Listen carefully. Listen carefully. I will explain this. So the Fermat's theorem work. Fermat's theorem gives the preferred remainder. First of all, what this theorem does? This theorem gives 1 as the remainder. The theorem, all right, now theorem, but applied on some special numbers. Special, all right, there should be some, there is a way to apply it. When you apply, you get the remainder as 1. Hey, what is this one? Preferred remainder. Therefore, you learn this theorem. If the theorem is not giving the preferred remainder, I am not interested. I am not interested. Therefore, Fermat's theorem I learn because it gives 1 as the remainder when there are certain conditions. Let's understand. First of all, your divisor should be a prime number. Your divisor should be a prime number. First of all, first and foremost, your divisor should be a prime number. Then base, all right, now you will have a raised to power b. Well, that's how your number will look like. But the point here is already a raised to power b. Technically, where the Fermat's theorem is applied, a raised to power b when divided by b, what is the remainder? What is the remainder? This is a functionality. What is this? Your number. What is this? Your divisor. All right, now, so what is a here? A is nothing but the base of the number. So what is the now? All right, now one thing. Divisor has to be prime. This was your divisor. Divisor is a prime. Second thing, a and p should be co-primes. A and p should be co-primes. That's important. What if they are not co-primes? You can't apply this theorem. Two checks. Your divisor should be a prime number. Checking number one. Second check, a and p should be co-primes. So what is a? A is the base. Base. You don't have to look at the power. Just look at the base. Now it gives authority to write the power. It doesn't understand the power b. But now the theorem gives the authority to write the power. What is that? If the divisor is prime, if the divisor is prime, a raised to power p minus 1, the remainder is going to be 1. That's the remainder. Remainder is going to be 1. When a, already know if p, a and p are co-primes. Whenever a and p are co-primes, raised to the power, it gives the authority to write p minus 1. That's it. All right, now look at this. This theorem has to be written reverse. All right, now you always start from the bottom. All right, that is when all conditions automatically get cleared. Firstly, write the divisor, which should be a prime number. Write the divisor, which should be a prime number. Write a base which is co-prime to this. Second condition, write a base which is co-prime to this. Write a base which is co-prime to this. Write a power which is 1 less than your divisor. Write a power which is 1 less than your divisor. Automatically remainder becomes 1. This is called Fermat's theorem. All right, this is called Fermat's theorem. Let me take a simple example. Fix a divisor. Let's say that I fix the divisor as 5. I fix the divisor as 5. Is this the prime? Yes. Write anything which is co-prime to 5. Is 2 co-prime? Yes. Raise it to the power p minus 1. Your divisor is 5. Write 1 less than that. Write 4. Divisor is 5. Write 1 less than this. Now look at the remainder. Remainder is going to be 1. I wrote very simple number so that you can understand. 2 power 4 is 16. 16 by 5. The remainder is 1. Hey, can I change it to 3? Of course you can change it. Let us keep the same divisor 5. Let's keep the same divisor 5. Let us write it as 3 here. Let us write it as 3. Now it gives the, are these two numbers co-prime? Yes. Alright, it gives the authority to write the power. Alright, now it gives the power. What is the power? 1 less than the divisor. You wrote it as 4. Remainder is 1. You can check that. 3 power 4 is 81. 81 divided by 5. Write anything co-prime to 5. Write anything co-prime to 5. Big, small, does not matter what you want to write. Write anything co-prime to it. Remainder always becomes 1. Alright, that is this particular theorem. I hope everybody understood this. Alright, internalize this theorem quickly. Let's see the applications. Let's see the applications. Internalize this. Internalize this theorem. Right? First, you should always start with the divisor. Divisor should be a prime number. Then you write the base of the number, which is a co-prime. Then it gives the authority to write the power. It does not understand b. In the exam, that may not be p minus 1. We'll come to that. We'll come to that point. We'll come to that point. Right? Great. Let's go to the example now. Let's take an example here. Let's take an example on this. Let's take an example. Okay, let's try this example now. All right, let's try this example. 2 raised to power 95 when divided by 19. Now look at this. All right, now what does the theorem states? Fermat's theorem states divisor prime number, perfect. Divisor prime number, perfect. All right, I write 19. That's my divisor. 2 is 2 co-prime to it. Yes, where is the 2 here? The base of the number. All right, 2, perfect. But the Fermat's theorem does not understand 95. What it understands is, hey, if you have 19 here, raise it to the power 18. Guaranteed remainder is 1. Guaranteed remainder. Alright, that is guaranteed. Yeah, what about this 95? It does not understand. What if 95? It does not understand. Now this is the Fermat's theorem. Alright, now you can say that I know this. You know this. I know that. You can start there. I know that this part. But the point here is what? I need to reach 2 power 95. You can't do what you wish to do. You know that 2 raised to power 18. But author is not interested in 2 raised to power 18. Author is interested in 2 raised to power 95. That is what his interest lies. Fair enough. So how do you do this? From here you have to reach. You have to reach. Now look at this. Say 2 raised to power 95 can be written as 2 raised to power 18 into another 2 raised to power 18. I'm just showing you in a detailed manner first time. Right? 3, 4 and 5. 2 raised to power 18, that is 90 by now. 18 into 18 into 18, law of indices, friends. That is 18, 18, 18, 18, that is 90. Or another 2 raised to power 5. I can write it like this. Isolation technique. Divide this by what? Divide this by 19. Therefore, divide by 19. Divide this by 19. Don't think that, okay, you are dividing by 19 raised to power 6. No. Technique of isolation. Isolate and attack. All right, isolate and attack. You're isolating. You have no intention of multiplying all these numbers. Isolate. Isolate and attack. From here, what is the remainder? 1, because that's what the Fermat's theorem said. 2 raised to power 18 when divided by 19, the remainder is 1. What is the remainder here? 1. What is the sign between them? Multiply. Therefore, 1. So what is the remainder here? 1. Therefore, you're writing 1 into 1 into 1 into till here it is going to be 1. Okay, 1. All right, till here it is 1 into what? All right, now this I do manually. 32 divided by 19, which is 13. All right, 32 divided by 19, which is 13. So therefore, what is the final answer for this question, which is nothing but 13? Okay, will I be splitting it like this? No, you will not be splitting it like this. Now listen carefully here. How do you consolidate this? Okay, let me write one step clearly here. So now you reach it here, 2 raised to power 18 when divided by 19, the remainder is 1. Keep this 2 raised to power 95 in your mind. Let's keep this 2 raised to power 95 in our mind. Let's keep this. Now I can write it as 2 raised to power 18 whole thing raised to power 5 divided by 19, the remainder is going to be 1 raised to power 5. Same. All right, the remainder is going to be the same number here. Hey, why did you do here? All right, you went with the stages of 18, 5 stages of 18, which went to 90. You went very, very close, which means you are trying to say that 2 raised to power 90 when divided by 19, the remainder is 1. Up to 90, there is nothing that is going to happen. Up to 90, there is nothing going to happen. Now, what you are trying to say? You are saying that I will multiply this by k, 2 raised to power 5, 2 raised to power 5. Why did you multiply? Because I need to reach 5. Then I need to multiply this or this side also. When a number is divided by a divisor, if the remainder is something, when 2 raised to power 2 power 5 is multiplied k times of the number, then the remainder also becomes k times of it. All right, therefore you wrote 2 power 5. Well, you wrote 2 power 5. Great. So, but then point here is what? Is this greater than the divisor? Yes. All right, therefore you can't give 2 power 5 as the answer. Divide by 19 here. You divide by 19 and you will tell the final answer as 13. Maybe this looks better. All right, this looks better than what we did before, which means we did this earlier. This looks better, far more better. Let's understand far more better. Focus only on the remainders. Why we need to do all this kind of, all right, too much of a job? Not required. Just focus on the remainder part here. Hey, what do you mean? All right, do it with me. I will tell you. 2 raised to power 95 divided by 19. So you know that already. You already know this. Go back here. 2 raised to power 18. Look at this particular power. What is this? 18. So just focus on that. Remove the cycles of 18. It's a cycle of 18. Why? Every cycle of 18 gives 1 as the remainder. Every cycle of 18 gives 1 as the remainder. You remove all the cycles. Like this 5 cycles were there. Remove 5 cycles because they anyway give 1 into 1 into 1 into 1. Why you are interested? Find out what is left after this. Nothing but a 95. You divide by 18 and list out what is the remainder here. The remainder is 5. All right, because 18 5 times is 90, remainder is 5. Therefore, you say that, hey man, answer to this is equivalent of 2 raised to power 5 divided by 90. Hey, what is that? Just the remainder of this. Just write the remainder of this. Don't try to tell me that 5 cycles I removed. I'm not interested whether you removed 5 cycles or how many cycles. I'm not interested. I'm interested in the remainder. Focus on that. All right, therefore, remove the cycles of 18. How do you know cycles of 18 should be removed? You should know the theorem. You should know the theorem. From the theorem, you will understand that cycles of 18 should be removed. You removed it, therefore your result becomes 13. Now, this is the working in the exam. Technically, this is the working I expect in the exam. You look 2 raised to power 95. 19, you will see it. 18 comes to your mind automatically. This theorem comes to your mind automatically. You don't have to write it. The theorem comes. Remove the cycles of 18 from there. You will be getting 2 power 5. And then you will be writing answer as 13. Very automatically. That's all the working that I expect. These are the 3 lines. These are technically 3 pieces of information that you might technically write in the exam. Right? Good. I hope all of you got this Fermat's theorem now. All of you have got this Fermat's theorem now. So I'll project the question. Try this, guys. All of you try this. Try this. Everybody try this. Try this. Everybody try this. You might have realized the answer is same, isn't it? So answer is same. So what you do here, all right, now, as I said earlier, 59. You will not even be knowing 59 square or whatever it is. Don't bother. First reduce it. Always make it smaller. All right, that's when you can handle it better. 59, all right, now divided by 19. Take only 159. Of course, there is a power 95. Don't bother. Always make the number little smaller so that you can work with that square of it, cube of it little easily. 59 divided by 19. 59 divided by 19, what is the remainder? 59 divided by 19. 19 three times. 57, therefore the remainder is 2. But the point here is a 59 raised to power what? 95. If you raise this to the power 95, this also should be raised to the power 95. This also would be raised to the power 95. Hey, is 2 power 95 greater than your divisor? Of course, yes. Then reduce it. Then reduce it. Nothing but the previous question. Nothing but the previous question. You look at this 19 divisor. All right, now from here you know that I know that. All right, from here you say I know that 19. 2 is co-prime to 19. P is prime. 2 is co-prime to 19. Raised to power 18. The remainder is going to be 1. The remainder is going to be 1. All right, remainder would be 1. Therefore, you say that I divide by 18. So again, back to the same thing. You get this as 2 raised to power 5 by 19. All right, result is going to be 13. Simple. All right, because you look at this 59, that's what they do in the exam. They make you a number like 59. The square of that number itself will be little bit, that will be frightening. Now, how do you find out 59 raised to power 5? You don't have to reduce it to 5. All right, technically, it's 2 raised to power 5. Why you are making it 59 raised to power 5? You don't have to. Right, first step is always reduce it. You get a number. All right, you have 19 here. You get the a. All right, if you get a greater than divisor, what is that? You have a power b by divisor, right? In this, if you get a greater than divisor, immediately ensure that you make this as an a dash less than divisor. You make this as an a dash less than divisor. How? Just do one division. You take this 59, divide this by 19, convert it to 2. First make it less than the divisor and then attack this question and then attack this question. These are the simple things that you should know so that it brings the effectiveness and the speed while you are doing in the exam. All right, simple things that you should know. Of course, you learn most of it by your experience as well. I'm just alerting you how you need to think while you're doing the problems. Great. Let's go to this question, friends. Let's take a look at this particular question. Find the remainder when 2 raised to power 93 is divided by 38. Now you say that, okay, I can't use the Fermat's theorem here. All right, because now the question here is 2 raised to power 93 divided by 38. Now you say that, is this a prime? No, that's not prime. All right, 38 is not a prime. Therefore, Fermat's theorem does not work. Yes, on the face of it, sometimes the things look like that. On the face of it, it looks like that. What you do is, whenever you get such situation, composite number, your divisor is composite. Don't bother about the number. Whenever your divisor is composite, first resolve it into primes. Resolve it into primes. What is this? This is 2 raised to power 1 into 19 raised to power 1. Perfect. All right, now you got this. So therefore, you can rewrite this as 2 raised to power 93 when divided by 2 and 19. So what do you do here? Treat a 2 outside. From here you say that, man, I will keep 1 2 outside in both numerator and denominator. Let keep 1 2 outside. Keep 1 2 outside. Then you write this as 2 raised to power 92. 2 raised to power 92 divided by 19. Hey, what did I do? I didn't do anything. I just treated 1 2 outside because there were 2 raised to power 93. I kept 1 2 outside. Similarly, I did here. Now I can apply the Fermat's theorem on this. Now I can apply the Fermat's theorem on this. What is that you are trying to say? 2 raised to power 92 when divided by 19. What is the remainder? 2 raised to power 92 when divided by 19. What is the remainder? Fermat's theorem. Divide the cycles of 18. Remove it. Therefore, it becomes 2 raised to power 2 divided by 19. Hey, what is that? All it remainder 2 raised to power 2 divided by 19. 4. Therefore, your remainder is 4. Technically, you are trying to say that 2 raised to power 92 when divided by 19. The remainder is 4. Very good, comfortable, very good. But the point here is I never asked you to divide by 19. I never gave you the number 2 raised to power 92. I gave you 2 raised to power 93. I asked you to divide by 38. What I asked is different from what you did. All right, now you did 2 raised to power 92 by 19. That is your fancy. All right, that is not what I asked you. Fine, no problem. So this is what you learned here. When the number is divided by the divisor, the remainder is r. Then k times of the number is divided by k times of the divisor. That's what we learned. When k times of the number is divided by k times of the divisor, the remainder also becomes k times. Perfect. That's what you did here. You said that you said that 2 that, hey, just stay away for a while. You are a k for me. I will bring you back in, buddy. I will bring you back. That's what you said. All right, that's what you did with this 2. That is nothing but my k. So bring it back. 2 here. 2 raised to 2 into 2 into 2 power 92. Was that the number that I gave you? Of course, yes. That's 2 raised to power 93. Bring the 2 here also. Is that the divisor I gave you? Of course, yes. 2 into 19. Therefore, what you should do here? Same 2 I need to multiply here. Therefore, you say that your final answer is going to be 8. Simple. All right, your final answer is going to be 8. That's the answer. Remainder is nothing but 8 here. So what you do is the same simple concepts. We just have to put them together and make it. See, on the face of it, this question looked like, hey, I can't apply Fermat's theorem. Why? You looked at the divisor, immediately immediately you said that that's a composite number. Hang on before you take the decision. So you just have to resolve it into prime, apply Fermat's theorem partially. That means you need not apply it on the entire problem, but can I apply it on a part of the problem? Of course, yes, part of the problem. And provided you can keep a k out, you can always bring it in. All right, remember, all right, now this particular, all right, remember these aspects. Don't shy away or move away thinking that my divisor is a composite number. Wait, all right, now wait, there may be a way, all right, you can apply the Fermat's theorem more often than not in most of the questions. More often than not, you can apply them. Right, great friends. Another 15 minutes. Another 15 minutes, I will do one more concept. Right, one more concept, one more theorem. Right, another 15 minutes. Another 15 minutes. Push yourself. Push yourself. You've been pushing so far. Push yourself. Another 10-15 minutes. By 9:95 we are done for dinner. All right, by 9:95 we are done with this particular lecture. So push. All right, last 15 minutes you push. All right, let's come to the Wilson's theorem. Let's take a look at the Wilson's theorem. Yeah, what is the Wilson's theorem? Wilson's theorem is for the factorials. For example, if you write n factorial, and I say that I divided by a divisor, tell me what is the remainder. I already told you one thing that we are not interested here is the quotient. Tell me the divisor. It's a pretty challenging one. All right, when you write it, it's a pretty challenging one. See, for example, right? So if you write 20 factorial, oh, it's a huge number. All right, it's a 20 factorial. So it's a number. Then I say that, hey, why don't you divide this by something, some divisor, say 23 or something. Then I will tell that, why don't you tell me the remainder? And now, all right, now this is a pretty challenging number. 20 factorial is 1 into 2 into. We can't write this, right? Now 2 up to 20, then multiply, divide by 23. Does not make sense. Or it does not make sense. Therefore, we learn a Wilson's theorem. Why Wilson's theorem? Again, it gives me a preferred remainder, which is -1. It gives me a preferred remainder. See, we learn theorems which gives the preferred remainder, either 1 or -1. All right, this again gives me a preferred remainder. Therefore, we learn this theorem. So there is an objective to learn certain theorems. When we learn a Pythagorean theorem, there is an objective. It is not that we simply learn theorems. All right, no, we simply learn theorem. There is an objective, especially like when we become adult. Right, as a child, probably some of the basics we do without really understanding why we are doing. But when we grow up, there is an objective before you learn anything. All right, yeah, especially the theorems, etc. So fine, the objective here, all right, now, so we are learning this theorem because it gives me -1. Let me understand, what does the theorem say? If the divisor is prime again, just like Fermat's theorem, the divisor should be prime again. Start with the divisor. Your approach has to start with the divisor, otherwise it does not make sense, right? Yeah, approach has to make all right, approach. All right, now here, so prime. So if you write p minus 1 factorial, if your divisor is a p minus 1 factorial, then the remainder is -1. Hey, but the final remainder, can it be -1? Of course not. Final remainder cannot be -1. Therefore, what is the final remainder? -1 plus p. -1 plus p. What is that p? Divisor, add divisor. No, if you are getting -1 as the remainder, you will not find an answer option as -1. What do you got to do? Write p, or let p there. So nothing but p -1. This is technically nothing but p -1. That's a number itself. Yeah, what is p -1? That's a number factorial. That's what you wrote there. Okay, let's understand this. Let me repeat it once again, friends. Let me repeat it once again. Listen carefully on this particular theorem. All theorem starts from divisor. Remember, all the theorems in remainder theorem starts from the understanding of the divisor. Your divisor has to be prime. I'm talking about the divisors which are prime today. I'm talking about the divisors which are prime. Fermat's theorem, the divisor was prime. Wilson's theorem, the divisor is prime. Yeah, are there theorems when the divisor is not prime? Of course, yes. Of course, yes. Right now here, all right, now let's write the divisor is a prime number. What you should be writing here? The number has to be 1 less than the divisor and its factorial. Because 1 less than that and its factorial. Your remainder will be -1. Remainder is -1. In other sense, clearly, if you want to write it clearly, you got to be writing it as p -1 or -1 plus p. -1 plus p, nothing but p -1. Let us take a simple example. What if my divisor is 5? Perfect. Divisor is 5. Write 5 minus 1 factorial. If 5 minus 1 factorial is divided by 5, the remainder is -1 or 5 minus 1, which is nothing but 4 itself. All at 5 minus 1, which is nothing but 4. Hey, what is 5 minus 1 factorial, friends? 4 factorial. What is 4 factorial? 24. 24 divided by 5 -1 because it is 1 less than 25. All right, which is a multiple of 5 -1, or you can write it as 4 because 4 more than 20. All right, 4 more than 20, that's 24. 5 factorial 24 is nothing but that. All right, 4 more than 20. Therefore, you can write as -1 or you can write it as 4. All right, that is what the Wilson's theorem states. Point number 1. All right, that is what the Wilson's theorem states. Point number 1. Let me come to point number 2. Remember this. All right, this is the Wilson's theorem. All right, Wilson's theorem. Point number 2. Let's do one question out here. Well, let's do one question out here. If I ask a question something like this, listen carefully. All of you listen carefully. If I write this particular question, all right, now let me write one of them. 18 factorial by 19. What is the remainder? Second question. 19 factorial by 19. What is the remainder? 20 factorial by 19. What is the remainder? All right, now here we already said that the remainder is -1 because this is the Wilson's theorem itself. All right, this is the Wilson's theorem itself. 18 factorial by 19, because the divisor is prime, minus 1. But minus 1 I will not accept as the final answer. Therefore 18. Hey, what is the answer here? 19 factorial by 19. 19 factorial by 19 0. 19 factorial 19 is 0, because when you're writing this 19 factorial 1 into 2 into 3, you're of course writing 19 here. So now you're saying that I will divide this by 19. This number is a multiple of 19. Remainder is going to be 0. Hey, what about 20 factorial? Remainder is 0. Why 20 factorial? Remainder is 0, because you are adding another number into 20. Is this a multiple of 19? Of course yes. Therefore, the point here is what? They will not go forward. When they give 19 here, when the 19 as the divisor, they will never ask a number greater than 19. Rather, they ask backward. Or rather, they ask backward. What is that? They'll ask 18 factorial. They'll ask 17 factorial. They may ask 16 factorial. What is that? They'll ask backward. There is no point asking forward. You fix 19, or you fix this 19, and then you'll ask 21 factorial. No brainer. Remainder is 0. Therefore, in the Wilson's theorem, remember, we move backward. In the Wilson's theorem, we move backward. That's a point I want you to remember. Right? That's a point I want you to remember. Fair enough. Let's go one step backward and check quickly. All right, one step backward and check quickly. Couple of things that you might have to remember here. All right, let me go one step backward and check here. Okay, so point number 1, we are clear about the Wilson's theorem. All right, point number 2. All right, now so let's remember this. 17 factorial by 19. What is the remainder? What is the remainder? Now listen, how do you work it out, these steps? You know what is 18 factorial. Therefore, you say that I know that. I know what do you know? 18 factorial divided by 19, the remainder is minus 1. You can write positive also. Can I write 18? No problem. Write one of them. Write one of them, whatever suits you. All right, whatever suits you. We'll take that final decision later. 18 factorial by 19, the remainder is this. Good. So all right, now this is what you know. But I'm not interested in 18 factorial. I'm interested in 17 factorial. Then make it visible. So therefore, from the same step, 18 factorial can be written as 17 into 18 divided by 19. The remainder is minus 1. Hey, keep this 18 in the mind. If required, we'll use it. Remainder is minus 1. Great. All right, you wrote this. So now this is nothing but whatever you wrote here, exactly same piece. You just split this 18 factorial and you wrote it 17 factorial into 18. Perfect. Again, isolate and attack, because you don't know what is 17 factorial. 17 factorial by 19. What is the remainder? Into 18 by 19. What is the remainder? Isolate. But I know the final remainder is minus 1. That I know anyway. All right, now what did I do? Nothing I did. The same information I don't isolate and attack. I'm bringing it to the isolation form. Okay, 18 by 19, preferred remainder minus 1. 18 by 19, remainder is this. Hey, what is the remainder here? Don't know. But what is the final remainder is minus 1. Point here is there is something here into minus 1. The answer is minus 1. What into minus 1 is minus 1? Of course, 1 into minus 1 is minus 1. All right, therefore, of course, 1 into minus 1 is minus 1 there. Therefore, you are trying to say that, okay, I need to fill 1 here. I need to write 1 here. Therefore, you got the answer for this. What did you do? Inferential. All right, inference. All right, you inferred. Therefore, 17 factorial when divided by 19, the remainder is nothing but 1. So, but directly remember it, friends. Directly remember, it's a standard result. P minus 2 factorial. Although Wilson did not say it, they're all derived. P minus 2 factorial when divided by P, the result is going to be 1. P minus 2 fact. This is a Wilson's theorem. The first point is the Wilson theorem. But we also know that P minus 2 factorial when divided by P, the remainder is going to be 1. All right, that's a point number 2. All right, point number 2. So which means, can I say that, hey, 81 factorial divided by 83? Answer 1. 81 factorial, answer is 1. Is 83 a prime number? Yes. All right, 83 a prime number? Yes. All right, 81 factorial. Is it P minus 2 factorial? Of course, yes. Therefore, the result is 1. All right, result is 1. Okay, that's a point number 2. Point number 3. Point number 3. All right, let's say that, okay, what if I go one more step further? All right, I went to 17 factorial. Let me go to 16 factorial from here. 16 factorial. 16 factorial divided by 19, what is the remainder? 16 factorial divided by 19, what is the remainder? Fine, so you can start at any stage. Can I start from 17 factorial? Yes, you know P minus 2, right? Start there. 19 is there. 17 factorial when divided by 19, the remainder is 1. No problem. What is the negative remainder? Minus 18. Negative remainder is minus 18. How did I get the negative remainder minus 18? If the positive remainder is 1, subtract the divisor. What is your divisor? 19 is your divisor. Here, 19 is the divisor. You get the negative remainder. Positive to use or negative to use, we will see it later, but keep it in your mind. Whenever there is a positive remainder, there is a negative remainder also. What comes handy can be decided at the later stage. What comes handy can be decided at the later stage, but be mindful about it. Be mindful. There is a positive window. There is also a negative window. If the positive window is 1, there is a negative window which is -1. What is this you started with? You started with, I know that. You don't know about 16 factorial, but what do you know? 17 factorial, you know. 17 factorial by no, it by 19, answer is 1 or -18. Fair enough. All right, now the remainder is 1 or -18. Good. Let's see that because I want 16 factorial, then split it to write just 16 factorial. 17 factorial can be written as 16 factorial into 17 by 19. Therefore, the remainder is 1 or -18. Let's keep that 1 or -18 as 1 for now. When if -18 is required, we will take it. We will take it. All right, that's how you are writing it here. What did you do? Nothing. You just change the form here. Change the form. Next step. All right, next step that you are doing here. 16 factorial by 19, isolate and attack. What is the remainder? 17 by 19. What is the remainder? You said that the final remainder is 1. No problem, keep it. All right, now from here 17 by 19, remainder -2. All right, now here some remainder will come. From here I will write some remainder, don't know. Final, all right, now into final answer should become 1. A -2 into something, writing 1 is little difficult. Therefore I will not write 1, rather I will write -18. Rather I will write it as -18, because -2 into something making -18 is easier. Use the window, because you have to arrive at the answer. All right, don't be rigid that no, I want to use 1 only. Then you have to apply Chinese remainder theorem on this. Now to answer Wilson's theorem, you have to apply another theorem. So don't bring another theorem to answer one theorem answer. Right, therefore you make the life simpler. All right, look at the other side of the window. Other side of the window is saying that it is -18. If you don't want to use 1, you can also use -18. Fair enough. -2 into something is -18. What is that? -2 into 9. Therefore you derive the result. Therefore 16 factorial when divided by 19, the result is 9. That is, remainder is 9. So therefore this is also a standard result. P minus 3 factorial when divided by p. Remember, the result is p minus 1 by 2. Remainder is p minus 1 by 2. Hey, what is p here? 19. All right, what was p minus 3? 16. Therefore the answer is 19 minus 1 by 2. All right, now which is 18 by 2, which is nothing but 9. Another example quickly on this. Say for example, if I have 80 factorial divided by 83, what is the remainder? It's of the same form. This is p. All right, this is p, and this is p minus 3 factorial. This is p minus 3 factorial. Result is p minus 1 by 2. Result is p minus 1 divided by 2. So what is p? 83. 83 minus 1 divided by 2. Result 41. All right, result 41. That will be the answer here. All right, 41 would be the answer. Now these are the 3 points I want you to remember about the factorials. These are the 3 points I want to remember. Let's take a cat question. All right, let's take a cat question here. Let's take a cat question with this. Then we'll close. We'll close with this. I'll give a minute, then I will solve, and we are sorted. With that, we'll stop. Yeah, here we go with the Wilson's theorem. One application, we understood the theorem. Let's apply it here. Take a minute. Here we go. Find the remainder when 100 factorial is divided by 97 square, right? 97 square. See, had it been 100 factorial divided by 97, had it been 100 factorial divided by 97, remainder is 0. All right, remainder is 0, no doubt. All right, 100 factorial by 97. But the point here is it is 97 square. It is not 100 factorial by 97. It is 100 factorial by 97 square. What is the remainder? That's a question here. We need to be mindful. If it is 97, then the answer is 0. Remainder is 0. Because then while writing 100 factorial, 97 comes. 97 is a prime number. But does 97 come twice? No, it comes only once. Therefore, how do you write it? Just like you learned earlier. Keep 97 away. 197 and 197. All right, 97 and 97, because there is a 97 here. Also, there is 197 here. Treat it out so that I'll be able to apply the theorem. Otherwise, because 97 square is not a prime number, therefore you look at it and you will say that I can't apply the theorem. All right, because is 97 square a prime number? Of course not. It has 3 factors. All right, it has 3 factors, right? Therefore, that cannot be done. It's not a prime number. But is 97 a prime? Yes. Therefore, what you do? Keep it away. You tell them that, hey, 197, please stay out. You are like a k for me, k. All right, k times of the number by k times of the divisor. You tell them that I will come back to you later. Keep it away. Keep it away. Then what do you look inside? Inside you will look, it is 96 factorial. 97 has gone. You are looking inside 100 factorial now. 97 is kept outside. 96 factorial is there. 97 is not there. 98 is there. 99 is there. And 100 is there. Hey, what is the divisor inside now? 97. What is the divisor inside 97? Why? Because another 97 has been pulled out. Another 97 has been pulled out. Okay. Now you think that where is the Wilson's theorem here? On the factorial. The here lies the Wilson's theorem. Okay, now what do you do? Isolate and attack your four elements. Isolate and attack. Don't try to multiply them. So what do you mean? 96 factorial by 97. What is the remainder? Into 98 by 97. Let us find the remainder. 99 by 97. We'll find the remainder. 100 by 97. We'll find the remainder. Let we'll find the remainder. What did I do? I am isolating the bracket. So what is there outside? K is there outside as it is. That K is there outside as it is. Great. All right, now from here 96 factorial. This is where you apply the Wilson's theorem. Only on this. Only on this. 97 is a prime. 96 factorial by 97. Remainder minus 1. Minus 1. Hey, can I write 96? You can write it small so that multiplication is easy. All right, so that it's easier. 1 minus 1 into what is the remainder from here? 1. 98 by 97. Hey, what is the remainder from here? 2. Hey, what is the remainder from here? 3. All right, remainder from here is 3. All right, therefore the entire thing is divided by what? 97. Hey, what is the remainder? Finally you got minus 1, 1, 2 and 3. You are saying that minus 6 is the remainder. You are trying to say that okay, when this element was divided by 97, the remainder is minus 6. You are trying to say that it's minus 6. Good. Therefore what is the positive remainder? What is the positive remainder? Positive remainder is minus 6 plus 97, all right, which is nothing but 91. You are trying to say that this bracket is giving me 91 as the result. Okay, let's go back to that earlier proposition that we started with. What did you say? 96 factorial into 98 into 99 into 100 when divided by 97. This bracket, friends, I'm talking about this bracket. All right, this bracket, the remainder is 91. Remainder is 91. But what did I do? I never gave you 97 as the divisor. I gave 97 square. Fair enough. All right, now put this K here. All right, this K's are there. Your 97s were kept outside. Your K was kept outside. Bring it. 97, you bring it back. 97, you bring it back. That has become 97 square now. This has become 100 factorial now. Therefore, what if you multiply this by 97, multiply this by 97, this also you multiply by 97, which becomes your answer. 91 into 97 is your answer. All right, 91 into 97 is your answer. Why? Will this be less than 97 square? Of course, yes. 91 into 97 is less than 97 square. So here you will be knowing you will be already in one of the speed lecture classes or here or there. You would have learned it already. You will use the deviation method. 91 into 97 deviation. You take 100 as the base method you will learn, right? The 100 as the base. Minus 9. Deviation is minus 9. Deviation is minus 3. Multiply the deviations, which is 21, right? Multiply the deviation, which is 21. 91 minus 3, which is 88. All right, now therefore you will say that 88 to 21 is the answer to this question. Remainder. Therefore the remainder is 8821. 8821, which is less than, of course, 97 square. All right, therefore this is your answer to the question, right? This is the answer. Okay, we are well bang on time. So here we go. All right, now this is about some of the things that we learned today, right? So we started off with finding the units digit of the number. Then we talked about the factors. All right, 3 important things about the factors we learned. All right, that's nothing but finding the number of factors, finding the sum of the factors, expressing the given number as the product of 2 factors. Then we learned about the remainders, properties of remainders, and 2 important theorems when the preferred remainder is not immediately visible. What is the preferred remainder? 1 or minus 1, but is not immediately visible. We learned 2 theorems with respect to the prime divisor. If the divisor is prime, we learned how to deal with this. Right, here we go, friends. All of you have a great day. I will see you with the next lecture. All right, bye till then.